Hello, good evening, everyone. Hi, Supriya.
Good evening, ma'am.
Hi, how are you?
I'm fine, ma'am.
So you are working day today for you?
Yes. Working day. I was telling same thing to Meghna. Today working day for us. So I had class till 4. Now I am coming from class.
Okay. Yeah, working for us also.
Yes, because of this 5 days week, so we have less number of holidays here. Happy Ram Navami, ma'am.
Oh, happy Ram Navami to all.
All the participants.
Yes,
Bajua.
happy Ram Navami. Yeah.
We can wait for another 5-6 minutes.
So before actually start, I think, we can have some interaction. So to all the participants, hope you're IGS members. I don't know. So if you're not IGS members, I would like to bring it to your notice. We have a student membership and also life membership. Meghna, I'm audible, right?
Yes, ma'am. Yes, ma'am. You are.
Yes, ma'am.
So
Yes.
please take the membership because we have a journal which is a SCA journal now. And then we have student chapters, lot of events, so goes on. And internationally also, we do have a lot of scope for our students. Recently for 17th ARC, we have given a lot of, the registration fee waiver for the IGS life members. Some of you may have papers also. In addition to that, Plaxis 2D and 3D has been procured by the society. And so it is like, from if your institute doesn't have it only for academic purpose, you can always take that also. So I want all the students to make use of the available facilities, whatever we have it at present. And if you need any other help or support or information, you can feel free to contact me, because right now it's actually basically trying to support for students. So mostly master students and research scholars. And the job openings are also being published regularly in every issue of the IGS newsletter, which is very, very helpful. And even some of the companies, they are just putting it up regularly. So a lot of information is there with the society. So it is a very vibrant society. So if you're not a student member or life member, whatever it is. So now this is our 75th year of celebration. As a part of 75th year, 25% concession is also there on the life membership. So I think this year, if you take membership, you have to pay only the 75%. Of course, this information just decided in the last DC, which will be circulated. So if you're not members, I think taking membership this year will be very advantageous. So because you get 25% discount, which will be around 3,000 around something. So with that, I'll just, sir, good evening.
Yeah, good evening, Nilima.
Sir, since time was there, I was just telling the participants about IGS.
Yeah, that's good. That's good. It's really good.
Good evening, sir.
Good evening,
Supriya, please say.
Supriya. How are you?
Fine, sir.
It's very nice.
Yes, ma'am, you can continue.
Yeah.
So nothing much, Supriya, because our website is also going to be very dynamic now. I think, they can participate and see network.
Yes,
Network
yes.
is something very important, and that can happen with the society. We have so many awards also. So we have best PhD thesis award and also best PhD thesis award from the universities. So we have two categories annually, and several research paper awards of IGS. So many times, many students are not aware, especially, students from NITs or other universities, they're
Yes,
not
yes,
aware.
true, ma'am.
So I think, please follow this web page of this. It is going to be, very dynamic new website is going to be launched very soon. But whatever information you want it, you can feel free to contact IGS office, or like I'm always there, or any of my student, because all of them are members. So you can contact anybody. We'll try to help you.
Ma'am, shall we wait for 2-3 more minutes?
Oh, sure.
Because 29
I think they
is
may be
left.
joining, and
We
today
have
it's a
more.
holiday for some of them, right?
Yeah.
No worries. We'll wait for some time. 5 minutes, we can wait.
Yes,
Ji,
yes.
ma'am.
Yes.
Supriya, if you want to try your presentation, you can try meanwhile.
Okay.
Nikhil, can you make Supriya madam the co-host?
Ma'am, she's already a host, ma'am. I have made.
So it's 4:35. Sir, shall we start? Maybe others may keep joining.
Yes.
Sure, we can start.
Sure, sir. Okay.
Sure.
So, Supriya, good evening. Dr. Supriya, I welcome you for today. First of all, thank you so much for being part of this 5-day event. And Dr. Supriya, I know because we were together at IIIT Hyderabad, sir. So she joined and she was there maybe for a year or so. I don't remember. Yeah, but we had a great time. So, and so happy that I would like to host you in person, Supriya, but that could not happen. Try to come sometime.
We can plan some event, ma'am.
Yes. You can come. So thank you so much. And first you have around 1 hour, and then we can have some Q&A questions from the speakers, because for the last 3 days, it was been very extensively taken care by Reddy sir. So it was very interesting, and I could learn a lot of things in personally. So I mean, a very good response from the participants also. So hope to listen to you. So thank you so much. Over to you, Meghna.
Yes, ma'am.
Thank you so much, ma'am. Thank you.
Okay. Thank you so much, ma'am, to provide me this opportunity to introduce Supriya ma'am also. Like Dr. Supriya Mohanty is working as assistant professor in Department of Civil Engineering at IIT BHU Varanasi. She received her PhD degree in civil engineering from IIT Kanpur and her BTech degree in civil engineering from Veer Surendra Sai University of Technology, Odisha. Her fields of research interest are liquefaction potential evaluation, soil dynamics, geotechnical earthquake engineering, and waste utilization. She has produced over 57 publications in peer-reviewed journals and conferences. Her honors include the ISET Shamsher Prakash Early Career Research Award by ISET Roorkee, the Early Career Research Award by SERB, DST, Best Researcher Award by VD Good Professional Association, and Young Scientist in Civil Engineering Award by Venus International Foundation. She has been received University Gold Medal, Achyutananda Pujari Memorial Gold Medal, and University Silver Medal during her BTech. She is a life member, associate member, and member of various professional associations such as American Society of Civil Engineers, Earthquake Engineering Research Institute, Institute of Engineers India, Japan International Cooperation Agency, Indian Geotechnical Society, ISSMGE, Indian Society of Earthquake Technology, and Association of Consulting Civil Engineers. Thank you so much, and I welcome you, ma'am, to give your lecture, and thanks for accepting our invitation. Please, sir.
Thank you, Dr. Meghna, for the introduction. Okay, is my screen is visible to you?
Yes, ma'am. Yes, ma'am. You can make it full screen. It is visible.
Okay, now?
Yes, ma'am.
Okay.
Definitely fine.
Good evening, everyone. All the participants. Happy Ramanavami to all of you. And I would like to thank first Nilima ma'am for her invitation. And surely we'll plan some offline event so that we can interact in person. So today I thought of discussing with all the participants to address a local problem, particularly to Varanasi city. So study on utilization of municipal solid waste fines like MSW fine fractions for various geotechnical purposes. So this study, it has been done by one of my PhD students, Parul Rawat, and her thesis has been evaluated. I am greatly thankful to Reddy sir for evaluating and giving valuable comments. So we will try to include that in our future scope. Thank you, sir. And before starting the presentation part, first I'd like to discuss being a human being and firstly civil engineer. We should understand the problem, our current problem, and what is our responsibility for the society. So I think most of you are MTech or PhD students, a few might be scholars or postdoc or faculties. So all of us are handling many real life practical problem in teaching and research. So while addressing that, we need to think a little bit. Can we address our local problem? And being a civil engineer and particularly geotechnical engineer, we should know what is the current status and means problem it is going on in our country and particular to your locality. If you can contribute a little, it will be really helpful, and we can means contribute towards our society. So as we all know how fast our population is growing, not only in our country, if you consider the world. So means we have limited space, that we know, and the population is increasing exponentially, that also we know. As the population is increasing, so our requirement means and waste it means generation of waste is also increasing day by day. So space is limited. Population we can't stop. Obviously, in near future also it will increase. So waste generation also it will increase. So means being a technical person and civil engineer, our responsibility is to think this whatever the waste we are generating, this is our waste. We should not blame कि somebody has done this for means in our city or means in your country, whatever the status currently. We should admit this is our waste. We are only the person and people, we are generating it, and it is our responsibility to think for its utilization and how we can contribute a little bit for means providing any technical guideline or solution to means utilize the waste, any means. Okay, so this particular study, I would like to means address like, and also thank Parul. She has decided and she has identified everything, even for sample collection and everything. She has first she spent nearly 6 months time to see the local what are the problem. And you know, Varanasi city is a very old city, and the means area is also, city area is also very small, and population is also increasing day by day. You know why it is so, because of this means religious place. So means that we can't also stop. So we thought of, let us try to find the means this MSW waste utilization study, and what is the current state in our particular Varanasi city. Let us try to find out.
So Priya,
Yes.
you are still on the title slide.
Yes, sir, I'm moving further.
Okay. No, that's
So
okay.
we thought of addressing the means MSW utilization in Varanasi city. So I thought I will try to introduce in this means particular presentation what is the problem already we know, then different landfill mining techniques and characterization of landfill materials, and I will move to the Varanasi dump site and particularly our case study results and possible application what we suggested, and it is going to be implemented in the one of the dump site means close to our IIT Varanasi. So already we had discussed means what is municipal solid waste, and this is the waste we are generating it. So it is composed of domestic waste, commercial waste, construction demolition waste, waste from our institute, hospital, and many other means nearby like municipalities area. So combining all, we are considering this as municipal solid waste, and the composition of waste also it changes from city to city and country to country also. If you see this slide, so here you can see the composition means world waste composition. Nearly 44% is biodegradable material, and if you see the right side part, this shows the just a minute. So this shows the Indian scenario of our waste composition of our Indian municipal solid waste. Here, the biodegradable material is nearly 47.5%. So which includes mostly food waste and green means waste. So, and in addition to you, if you can see here, nearly 25% is inert material. So it is our responsibility how we can utilize this huge percentage of MSW in useful applications, particularly in construction or any means useful material. And if you see here, this shows the world waste production and GDP. So if you can see here, considering top 20 countries, so if you see here, we are at the third place. So this shows our GDP, and this shows how much waste we are, particularly MSW, we are generating. So means that way also we can compare. Means currently we are in lack in the mitigation technique, or means management technique of MSW. So we need to think of. Then the problem with this urban solid waste management, particularly in India, is means we don't have means proper integrated waste management technique. If you compare with other country, Reddy sir is here, he also can means address the same. So if you compare our means MSW area with other country, then you can see the variability and the means management technique also. And for this we also need the support from our government. Now at least many means initiative has been started, like Clean India Mission, Swachh Bharat Abhiyan. So we are getting fund to means go for suggesting for such mitigation or management technique for waste management, means solid waste management. So if you see this planning commission report of 2014, there you can see nearly 471 millions, which is about 34.5% of total population. They are residing in urban area and generate 62 million tons of MSW per annum currently, and it is projected that by 2031, these urban centers will generate 165 million tons of waste annually, and by 2050, it could reach 36 million tons. So we can means imagine how much area we need to means dump this much of waste by means 2050. So it has been estimated nearly 43,000 of hectares of land we need only for dumping this means MSW waste, means solid waste. So the collection efficiency is now means 70 to 90% in major cities, but while below means if you see below 50% in several small cities, even here Varanasi city also I can say it is means below 50%. So this is because we are giving very means low attention to scientific, towards the scientific and safe disposal of waste, and there are only 59 constructed landfill sites in India, and 376 are under planning and implementation. 1,305 are identified for future use. This is just for Central Pollution Control Board 2013 report. So if you see this one as per 1920 report, so this is the status now. It has been improved a lot, but here you can see this one, the total number of existing dump site is nearly 3,151. So dump site means already wastes are there. So you can see the number here and what is the plan, and this figure represents means whatever landfill constructed and under construction and in operation. So whatever landfills capped, so that information is given, and this can be found in your this Central Pollution Control Board report 1920. You can get online. So we need to think for this much of means whatever already it is existing dump sites are there, how can we utilize? So the solution. So what could be the solution? The first solution, what we can think, we can try to minimize the waste at the source location itself. So at your source point, you can try to reduce the waste. Second, to understand the type of waste. What type of waste is generating now? If you compare our waste with other country, definitely you can see, like second slide, I have shown you the composition of world MSW and our Indian scenario. So you also currently you should admit India is changing from agricultural based to industrial and service oriented country. So the waste characteristics, whatever the solid waste, the properties also it will alter due to the means change in living standard and increase in commercialization or urbanization. So this also we need to understand, and we need to address this an efficient waste management system, like whether we have a efficient management system for our particular city that includes like segregation unit, transport system, monitoring and investment on infrastructure, including all. We need a integrated solid waste management system for the proper solid waste management. Next, it means with our hand, introducing new policy and technique through R&D. Based on your research and development, you can try to suggest or introduce some new policy or technique for the waste management, particularly solid waste management, and some scientific landfill technique also we can suggest. So landfill mining is nothing but like the excavation and treatment of waste from an active or inactive landfill for one of the following purpose, like whether you are using it means reuse of recovered material, or we are interested to conservation of landfill space because the space is limited. Now a reduction in landfill area, elimination of potential contamination source, and energy recovery from the excavated waste. Now because here in Varanasi one plant has been installed recently, waste to energy plant. It is also close to our institute. So from that side also we have collected a few fiber means waste material to study. So means how to generate energy from the waste, that also can be done, and site redevelopment, all that can be done. So if you look at the past study, whatever done means it has been studied particularly in India, many studies has been done on MSW, that is field and lab scale, but limited study you can find on fine portion of the MSW, that is soil like material. Field study means whatever the existing dump site is there, what is its behavior, how the site will behave, what is the strength characteristics of that particular landfill dump site, that has been studied. But fine fraction studies has been limited. Here also, as we know, the composition is very complex and heterogeneous in nature. So we need to understand its chemical and physical, even geotechnical and strength properties to suggest or propose for any geotechnical or even construction material. So very few practical application has been suggested, like Delhi landfill site. Now they have suggested, I will show you one slide. So then coming to our case study, so I will discuss the study done by one of my students for this Varanasi dump area. So what we have done in this study, so we have collected the MSW raw MSW samples from one dump site, landfill site, Ramana. It is close to our IIT BHU. And second, we have collected the rejected sample from this Karsada plant Varanasi. This is a waste to energy plant. So they are utilizing the waste to generate energy, and still they have some rejected waste. So we thought of utilizing this rejected waste to improve the properties of this fine MSW fines. So after collection of the sample, we thought of go for air drying, then screening by different sieves, and below 4.75 micron sieve, we considered that as soil-like material, and we have considered that for the present study. Then for the source, this soil-like material MSW fines, we have studied its physical, chemical, and geotechnical characteristics. Then based on the strength properties, we thought of utilizing the waste from the this another waste to energy plant, that is the 4 mm rejected sample, the fiber obtained from that second site, to use for the for improving the soil like material of the first MSW. So waste fiber, we are trying to utilize waste fiber to improve the properties of another waste, means another means same MSW waste, then obtaining the optimum fiber composition, and trying to study its response under different loading conditions. So objective is to check the chemical and geotechnical feasibility of this MSW fines as a geotechnical constructional material, and further improving its strength characteristics by using waste reinforced with waste fibers. And so research outline chemical geotechnical characterization, dynamic properties, strength, and means like static strength properties and dynamic strength properties of source MSW file and reinforced MSW file. So we are not using any additional geosynthetics to reinforce the MSW files. We are using the fibers obtained from the same MSW to strengthen its static or geotechnical properties. So this is the sample collection site, Ramana site. It is nearly 5 to 6 kilometers from our campus. So my students have collected the sample from here. Then we go for the segregation process, raw sample after air drying. This shows the segregation written on different sieves. And this portion below 4.75 soil-like material, we are considering for further study and possible application for embankment or subgrade material. Based on the properties obtained from this, we'll suggest. So here you can see the chemical characteristics of this MSW fine. So pH value is nearly 6.4, which is slightly acidic, and organic content 5.9. So the tolerance limit for organic content, it varies from country to country. I think for US it is nearly 7%. I mean, it should be less than 7, and for Australia it is less than 1. So, and the color of this MSW digit is light yellow color, which is little bit objectionable, and this chloride, sulfate, TDS content is marginal if you see the percentage. And in addition to that, we also have studied the chemical like elemental analysis, XRD, XRF, and EDX before this strength calculation, because we need to know whether is there any hazardous material present in the MSW fines or not. Otherwise, means after implementation in the field, it may also affect the surrounding soil and groundwater. So here you can see the EDX result. There are in addition to like carbon, oxygen, silicon, alumina, presence of iron and titanium. So these are like few heavy metals are present. We need to address this before final implementation. And here you can see the mineral like quartz is predominant in the MSW fines, source MSW fines. And this shows the compounds present, concentration percentage of compounds present in the MSW fines. So nearly 48%. This one means silicon dioxide, and if you see the this third one is your aluminum oxide, and 12.2%. So means and only problem is here you have some few heavy metals present. We need to address this and reduce this before final implementation. This shows the surface morphology image of this MSW fine fraction. Here you can see heterogeneity in the material. This particles like different shape particle you can see elongated shape, and non-uniformity you can find. So this is because our MSW menstrual solid waste is composition of different type of waste. So we can't have uniformly graded soil type material for such waste. So then coming to geotechnical characterization, as from the past chemical study, we found that okay, this material, it has the organic content and all within the permission limit. We can go for further geotechnical study so that further application or possible application can be we can suggest. So from geotechnical study, first we start with sieve analysis gradation. So here we found the material is silty sand type and non-plastic in nature, and specific gravity is found to be 2.32, which is quite lower than the soil specific gravity because of the presence of lightweight material in the fine particles, MSW fines. Compaction density MDD is 1.51, which is also quite good, and the consolidation properties like compression index 0.25 to 0.12, this with decrease in density. So sorry, increase in density, relative compaction we have varied for different relative compaction, and UCS test also we have performed, then triaxial test for strength parameters. So by varying the this density range from 95 to 99. Why we have varied this relative compaction from 95 to 99? Because we thought of utilizing this material, soil like material, for embankment fill or subgrade. So if you check the ISC guideline, so the compaction or relative compaction for this subgrade material, the relative compaction, it should be more than 98%, and if you are suggesting for embankment, it should be more than 95%. So we thought of including a wide range from 95 to 99, so that depending on the requirement, we can select the appropriate density. Then permeability and CBR test also has been done both for soaked and unsoaked, because CBR value we need for this embankment or road pavement application. This permeability value is also coming within the range of silty sand, and this shows the gradation curve for the MSW fines and the source field MSW samples before segregation. And this shows the compaction curve MDD 1.51, and this is the CBR value. Here you can see the soaked CBR value, it is ranging from nearly 14 to 20, and unsoaked is 10.2 to to nearly 14. So, but if you check the IRC guideline, means for subgrade material, the severe value is, I mean, recommended severe value is, it should be more than 10%, and for embankment fill, it should be more than 5%. So whatever we are getting for the present material, before strengthening it, the raw MSW sample is giving us means good severe value, which is also suitable for road application. This shows the permeability range. With the increase in relative compaction, permeability decreases. As we know, biot ratio reduces, so this will means permeability will reduce. And this shows the compression index variation with relative compaction 95 to 99. So, and here you can see the shear strength, means net shear strength variation with relative density. So if you see the C5 individual cohesion and angle of friction, so there is not much variation in means C and phi. C improvement is there, but friction angle improvement is not much with the change in RC. But if you see this resultant shear strength curve, so here improvement you can see with the increase in means relative compaction, and for the considered range of relative compaction 95 to 99. And conclusion from this chemical and geotechnical analysis of this MSW fine is without any fiber. So here we can see nearly 60% of the waste material is non-plastic, siltation type, and with medium compressibility, medium permeability, and it is giving us good shear resistance. So, and if you see the specific gravity 2.32, so low specific gravity, so made it suitable for lightweight fill material. And however, the concentration of the means few heavy metals and like organic content and color of the leachate, it could create serious problem if we will neglect in during the application. So proper treatment must be required, so before final implementation in specific project. So next means as this present study area is seismic zone 3. So we thought of analyzing the dynamic characteristics, because you know how frequently we are experiencing the earthquake in not if not in our country but in our neighborhood. So we need to understand the dynamic strength of this proposed material. As you also have seen in 2016 after the Nepal earthquake, our code has been revised. So we are waiting for another major event, then we will try to again improve. So in our revised code, there some guidelines has been included for liquefaction study and dynamic study also. So for that reason, we thought of finding the dynamic characteristics of this MSW fine, so that seismic analysis can be done for any structure, whatever the structure it may be, whether embankment or road or railway embankment. So we need to know the dynamic properties of the subsoil or foundation material. So we try to use the whatever the facility we have in our lab, cyclic Excel setup, to find the dynamic properties, shear modulus, and damping ratio. So this shows the setup available with us. This is the MSW sample, source sample without fiber. This is the cell, and this is the assembly, with mounted sample. So from this and here we have to apply this cyclic load by means of this actuator. So we can apply both stress and strain control. We have tried strain control, and from that we can get the hysteresis loop stress strain curve. From this curve we can get Young's modulus and shear strain, and then shear modulus and damping ratio we can get. So here for dynamic study, we have varied the density from 90 to 98%. This confining pressure, 3 confining pressure we try to change 50, 70, 100. This is because suppose for different depth, means low height embankment to high means greater height, the confining pressure also will increase. That's why we thought of changing, keeping the confining pressure from 50 to 100. So that at least we can have lateral confinement effect consideration. Then shear strain we have varied 0.4 to 1, loading frequency 0.3 to 1 for our study. This shows the typical cyclic results. This is the input axial strain, that is strain control test we have done, and this is the derivative stress variation with number of cycles. The derivative stress is decreasing with number of cycles. Here you can see the pore pressure is increasing, and this shows the hysteresis loop. So for dynamic properties, we need this stress strain plot. So this one we have used for calculating the G and D. So here you can see the effect of relative compaction and dynamic parameters. So dynamic shear modulus, here this plot you can see the dynamic shear modulus is decreased with the increase in number of cycle, which is obvious, and with the increase in relative compaction, there is improvement in your this dynamic shear modulus value, G value. However, this damping ratio is decreasing with number of cycle, but there is no proper trend. We are not finding random trend for damping ratio. Shear modulus stiffness is increasing with the increasing RC. So, but damping ratio it is there. This may be because of the heterogeneity of the material. And this slide here you can see the effect of confining pressure 50, 70, 100. So with the increase in confining pressure, here we can see the improvement in dynamic shear modulus. And for some cases there is improvement in damping, but here also a random trend has been shown for damping case. So for this type of this damping behavior, it has also has been addressed by a previous researcher. So due to the strain consideration, as we are doing a cyclic triaxial test for high strain condition. So for high strain condition, the damping ratio means it may means decrease with strain. It has been addressed by few researchers. So if you see the frequency effect is not that much affecting the strain. If you see the dynamic shear modulus, there is no means, significant effect of frequency can be noticed from this figure. So, and similar observation has also been noticed by past researcher for soil type material. Means silty sand also, not MSW, but silty sand. So this shows the strain influence or effect of strain amplitude on dynamic parameters. So if you see dynamic shear modulus G value is decreasing with strain as we are increasing the shear strain. So obviously the stiffness will reduce, and for all the cases, but damping variation is random. This is because of higher strain consideration and heterogeneity of the material. This slide here you can see this which factor is affecting most and which one is less important for your particular means properties. Like suppose if you consider the 4 parameters, composition or percentage of fine, confining stress, then relative density or unit weight, loading frequency. So for small strain shear modulus like Gmax, so the composition is most important, and confining stress and relative density or RC. However, the loading frequency effect is means insignificant, or you can say less important, both for this means small strain and high strain dynamic shear modulus. So if you see the material damping ratio, damping properties, composition is most important, and this confining pressure likely important, but unit weight and loading frequency not that much significant. So this has been reported by other many researchers for MSW side and sandy type material, soil type material. So conclusion from dynamic calculation of this source MSW fines. So here what we can see, out of the 4 parameters, whatever we had considered, relative compaction, confining pressure, frequency, and axial strain. So the dynamic shear modulus of the considered MSW fines is highly sensitive towards increasing frequency, increasing confining pressure, relative compaction, and also this has been validated with past researcher for similar type of non-cohesive soil. With the increase in strain, both G and D decreases, keeping other parameter constant, but trend of damping ratio versus strain means were noticed to be means different from the past researcher, because if you are comparing our result with past research, so past researchers they have considered low strain range, but our strain range is little bit high. Only few researchers they have considered both low to high. So from that, what we can notice, after 1% of means 0.5 to 1% of strain, the means behavior of damping ratio is random, and this similar type of behavior we also noticed. So this is due to the strain range consideration, heterogeneity, physicochemical characteristics of the material, morphological characteristics. From that we can see means different shape non-uniformity in the material. This is we can't means completely relate soil means MSW fines with our silty soil. The behavior is similar to silticide, but the composition, chemical characteristics will come different from normal soil. So loading frequency has no significant influence of strength, this G value, dynamics here more or less. Then after that, we try to find the or try to improve this shear strength behavior of the MSW fines by reinforcing with another waste fiber. So this MSW fines reinforced with fiber. These fibers are part of the collected waste from another this waste to energy plant, Karsada plant in Varanasi. So this plant basically it is a waste to energy plant, and from that plant also they are generating like 4 rejected samples. They are dumping it in the nearby site. So we thought of collecting this 4 rejected sample and trying to use the fibers to improve the MSW fines. So this is the 4 rejected sample collected from the Kasada plant and segregation process. And this is the final fibrous material. This fiber we are trying to use for improving the strength characteristics of the MSW fines. So we try to vary the fiber percentage from 0.5 to 10. So here you can see the compaction density MDD-OMC variation with the increase in fiber content. The density MDD is reducing and OMC is increasing. This is obvious because we are replacing fiber with soil. So fiber weight, it is lightweight, so the net MDD density will reduce. And this shows the stress strain plot for this different fiber concentration. 0 means without fiber, whatever we had earlier MSW fines. Then and this is 0.5, 1, 2, and till 10% we have value. So and here also we try to check two conditions by fixing the density, that is whatever the MDD of the original source material 1.51. Another one is whatever the density we are obtaining from this compaction curve. Suppose for 5% this is the MDD, for 1% this is the MDD, for 2% this is the MDD, and similarly for 10% this is the MDD. So this one represents varying density. Varying density means for different fiber concentration, whatever the MDD we are getting, for that we have tried to study the strength properties, C5. So for here, for both the cases, you can see after 8% of this fiber concentration, there is not much variation in friction angle. So based on this, we have considered this 8% as optimum. And here, and then we have compared 0% to 8% this optimum fiber concentration, cohesion, and angular friction. Here you can see in the improvement in cohesion and angular friction, and also the strain range. If you see the strain range, it is close to 20%. So it means with reinforcement, means this fibrous material, if you are using to reinforce the MSW file, it may allow more deformation, and you can see from this axial strain cohesion axial strain curve and friction angle axial strain curve. So conclusion from this fiber reinforced waste study, particularly static study we have did. So here the addition of waste fiber, that is optimum 8% by weight, the MSW fine shows remarkable improvement in the strength characteristics, which was noticed here, both C and phi improvement, and the considered material after reinforcement can be suggested as a embankment or subgrade material. Even without reinforcement also the material is giving good severe value and this shear strength, but after reinforcement the friction angle is improving here. If you compare source material, it is nearly 30. So with improvement, at least we are getting more friction angle value. So frictional resistance is increasing. So this material can be suggested as embankment or subgrade material. Then we thought of doing the dynamic strength characteristics of this reinforced MSW fines. So here we have tried to study both unconsolidated drain UU and consolidated drain test. So we have considered the test for a constant density, constant frequency, constant confining pressure by varying the axial strain. So for different fiber concentration. So here you can see the dynamic shear modulus G value variation with number of cycle for different fiber concentration and different strain, shear strain. So this one for 1.5% strain you case, and this one for 0.6, 0.9 and 1.2. So here what we are getting, there is no improvement in our dynamic shear modulus, particularly with the inclusion of this fiber. But static strength improvement is there. Both C and phi friction angle has been improved from 30 to 39. But here dynamic strength or stiffness improvement is we are not counting it. It is insignificant here. And damping ratio also similar to previous. So with the this shows the outcome of our reinforced study, dynamic study. So G value, it is decreasing with increasing fiber concentration, and damping ratio, it is showing random trend. So from this conclusion from fiber reinforced waste dynamic study, so there is no improvement in dynamic strength G value of MSW fine with fine content, and the degradation of the strength is comparatively low at higher strength. But here you can see degradation is low, but strength improvement is not there. So from this, what we can conclude, this material, it can be used for low risk seismic zone under even low to high embankment. But dynamic in high risk seismic zone, we need to improve the dynamic properties of the material, first strength properties, then we can recommend. But for like zone 2 or few portions of zone 3, it can be used for low rise embankment, low height embankment. So from that, based on our conclusion from static and dynamic study, as here there is no improvement in dynamic properties. So we thought of let us recommend the material to be used for embankment, road embankment. So we have recommended for this embankment for 4-lane road near the same Ramana site where we have collected the sample. So for that area we have recommended, and the soil sample from the same site we have obtained from this report. And by considering the existing foundation soil, subsoil properties, and whatever the MSW finds we have obtained from our study, we try to analyze the embankment problem using Fluxys 2D. So total top width of the embankment for 4-lane we had considered 16 meter, side slope 2:1, and the traffic load of 10 kilonewton per meter square. Low traffic load we had considered earlier, but it can be studied further. So water table, because for that the site, the water table was far below, we have taken the data. So it has been taken at 13 meter based on this report. Then these are the parameters. This embankment fill material is whatever the MSW finds we have obtained from our study, and these subsoil properties are for the actual soil profile of this Ramana dump site. Then after the analysis, static analysis, this shows the displacement profile, control field of displacement, vertical displacement, and this shows the variation of vertical displacement at different locations. So these locations here, we had considered 4 sections. One is close to the center portion, another one is this close to the slope, starting of the slope, one is mid slope, another one is end of the slope. So with depth, how the settlement or vertical displacement is varying, we try to analyze here. So maximum is observed for the center locations. And here you can see the total stress variation at different location, and this shows the for the whole domain control field maximum here. And here this one shows the horizontal stress variation, and this shows the shear stress variation at different location and control field of this same. And in addition to that, we thought of calculating the settlement, because we have the consolidation data with us. We have done the consolidation test for this MSW finds. So we thought of calculating the settlement analytically also. So from that analytical calculation, we are getting nearly 70.9, 71 mm of primary consolidation settlement. And if you see here, the vertical settlement from the numerical analysis, this is value is 55 or 56 mm. So analytical here we are getting little bit higher value because of this elastic properties consideration and many assumptions considered here. And conclusion from numerical study, what we can conclude, the total settlement, whatever we have calculated theoretically and numerically, it is found to be below the allowable settlement recommended by IRC 75 1979 for design of low embankment. That is, the allowable settlement is 300 to 600 mm, and we are getting even from analytical means expression 71 or 70 mm. So without any treatment, the settlement value is within the permissible limit. So for particularly for low embankment, even if we go for high rise embankment, this means range may change, but we need to check. So we thought of at least let us suggest for embankment fill material. So and for this Kastura side also, they are planning to do the means nearby road, low traffic volume road using the waste means obtained from that plant, and based on our test result report, because we have taken the sample from their plant, we have given the report. So they are going to implement the nearby plant site area. So concluding remark from our study, because the study particularly focuses on the how to reutilize the waste portions, particularly MSW fines or reinforced MSW fines in various geotechnical purposes. So the sample can be suggested to use in low seismic zone, because a high seismic risk zone, the dynamic strain should improve, but we are not getting for the considered fibers. If we use means other material, we need to think of how to improve the dynamic properties of this means MSW fines for utilizing in seismic means high seismic risk region. But current state, it can be used for low seismic risk, seismic zone, embankment and backfill subgrade material with low dynamic load in small projects, because we have good compaction properties and severe value strain properties also. However, before final implementation, we need to means at least improve these chemical characteristics of this means MSW fines. Few treatment may required, and after the treatment, it can be final. So means based on the chemical composition or chemical characteristics outcome, you need to decide which one we need to means choose for your improvement. Either you can mix the MSW fine with local soil or any lime to balance the means pH value, and to reduce the color effect, you can wash it. So and or we can use any means separation like liners, means so that the whatever the leachate it should not propagate or it should not contaminate your water table. Then future this possible utilization of this or reuse of this particular soil like waste or MSW fine fraction after treatment, obviously. So accepted waste, first we need to go for segregation and screening and segregation. Then we will get the MSW fines. Treatment, depending on your chemical characteristics results, you need to select appropriate treatment technique, then potential use. So that also depends on your application. It can be used for construction material. From our study, we are recommending as fill material, embankment feed, and sub-base material. And one means Ramana said they are going to implement it. And the proposed utilization scheme for MSW fines in past study, this you can see many other countries, they are also utilizing this soil-like material. Here I am talking about only fine fraction soil-like material as a means landfill cover, and if you compost for, and also few cases you can see here like they are using means a sub-base material, and most of the cases landfill cover material. And in Delhi, Gazipur area, they are using as embankment fill. And if you see this one dominant side, we are suggesting as embankment fill. So recently, National Highway Authority of India, in the month of February, last month only, so they asked the Municipal Corporation of Delhi to provide 364,000 tons of inert material for the construction of urban extension road to project. So they are going to utilize 364,000 tons of garbage from Gazipur and Okla landfills, means for the road construction. So this is national highway. So here you can see, previously they have recommended for embankment fill, and based on their observation now, means at least Indian government, they have planning to utilize the waste in national highways. So we need to think different applications where this waste can be utilized. And here in this study I have focused on MSW fines, but there are many ways we need to think of how we can utilize it, because we can't reduce. We know we can't reduce. As the population is increasing, the waste generation also it will increase. Thing is how to manage it, proper management and utilization. So this is our responsibilities. So we need to think of, and being a geotechnical engineer and research scholar faculty, this is our duty and responsibilities to find the solution for this. These are the few references. And finally, what I would like to say, this is the only safe home we have. So it is our responsibility to maintain it and keep our environment clean and environment sustainable. Thank you all. And we have time with us. We can discuss, and thank you.
Thank you so
Supriya.
much.
So we can have some question answers from the participants.
Very
Yes.
nice presentation, Supriya.
Thank you, sir. Thank
Yeah,
you.
very comprehensive. So
Thank you, sir.
very good, very good. So maybe hopefully you can do some field pilot testing also. Maybe you can construct a embankment somewhere and monitor it.
Yes, yes, it is.
Demonstrate in the field that what you are suggesting is actually feasible.
Yes, yes, yes. Actually, for that Ramana side, we have recommended, and that waste to energy plant they are using for their nearby road. So not for NH, but at least village road they are trying to implement.
Yeah, I think if they're implementing for an embankment, for access road, maybe you can just monitor that one. I mean, just work with them and see the construction process right from the beginning. Characterize the waste that is going in there, and then
Yes,
monitor the settlement and other things. And then one always, like environmentalists talk about any kind of environmental impacts, you can put a lysimeters at the bottom and try to collect the liquid and show that it's not a problem, or if there is a problem. I think that will be really great.
It is means the site is close to our campus, so it can be done.
Yeah,
I will
exactly. That's nice.
Thank you.
So what is your experience with the waste to energy plant that you have? You said there were some rejects. What was the reason for the rejects? Why some of the waste was rejected by the plant?
Actually, I think they are telling this is very heterogeneous. I'll show you that sample. So they are telling for our plant, like production, we don't want this type of material. 1 minute here.
Fine,
this
sir.
one.
Fine.
Is it? Yes, this type of material. So they are trying to dump it in nearby site. So we have suggested why you are dumping it, at least use for your nearby road means construction. So field severe value they have done by us only. So and for actual like low volume traffic road we have recommended, as you have suggested. I will discuss with them to when they will start the project. Before that, at least let us know, we can start the monitoring.
Very nice, very nice.
So there are no questions, sir. Shall we move on?
Yeah, they might ask questions at the end, maybe. I'm not sure.
Okay.
Good evening, Supriya ma'am.
Yeah.
Good evening.
Am I audible?
Yes, you are audible.
Ma'am, it was very good presentation. I just would like to ask a question about that.
Yes.
Since you have worked over the MSW fine particles as a soil materials, it looks to be a chemical analysis quite less, since you are also proposing to use it in the embankments. So heavy metals and any other uh, contamination or that kind of testing, is it feasible to use that in embankments?
See, for embankment, means our water level will be below the ground. So means the whatever the basic test required that we have calculated, means as per our total provision. So we need to check the pH, what is the means nature and organic content we need to have. So that percentage and the chemical composition, or whether heavy metal is present or not. So for heavy metal concentration, you should have EDX results and XRD, XRF. That much we have done, but in addition to that, what you are suggesting, we also need to do a few more additional chemical characteristics, because means I mean rainy season, the means it may propagate till or contaminate the water table, or what I will suggest means like liner or some lining material we can use, so that we can prevent that contamination effect. But additional chemical study is needed. As I have said in the last slide, this is based on strength and means strength characteristics behavior. But before final implementation, if you see, we need to means study further for the chemical part. This one. So obviously, as there is heterogeneity in the means MSW composition, so there may be chance that heavy metals are there. So we need to reduce and means before field implementation. So pre-treatment is needed. And also monitoring, whatever Krishna Reddy sir has addressed. So we need to monitor whatever we are getting, because whatever we are studying, it is in control environment, lab scale. So, but in actual field, whether same thing means they are going to maintain or not, we need to monitor that. And we know our scenario in India, how to means maintain the quality control. So it has to be means pre-treatment is must, means chemical treatment is needed.
Thank you for your answer, ma'am. Just one basic question also, maybe you have informed, I have not get that. Ma'am, how much this MSW fine material you get from the overall waste that you have got?
60 is nearly 60%.
It's nearly 60%. Okay. Thank you, ma'am.
Okay. You're welcome. All the best.
I was just looking at the chat also if there are any questions. So
Okay.
I don't see any question there. Okay, sir, if there are no questions, shall we wait or like proceed, sir?
No,
We can proceed if you want.
Sure, sure. Okay, sir. Thank you. So thank you, Supriya. It's a
Thank
nice
you, ma'am.
presentation. Thanks for having you. We are very happy to hear to you. So thank you.
Thank you, sir.
So we'll move to our second presentation by Professor Reddy. So so I request sir to take over.
All right. So let me share my presentation. So before I start presenting, I'm going to reference several publications in my presentation. It's not possible to explain a lot of details. So what I want to do is I want to give you a link to the publications, like I did it in the last webinar, yesterday's webinar. So don't get panicked if you want to look for a publication that I'm going to reference on my slides. So this is the website where you can find all the publications. And I also want, before I start, I want to mention that I organize a weekly geoenvironmental webinar series on Thursdays, Indian time, 7:30 to 8:30. So right after my presentation, that's going to be there. And I don't know how many of you have attended these webinars before, but we need to I need to, finish my presentation and moderate that other weekly webinar that I had organized. So if you are interested in attending that webinar, the details of that webinar, I'm going to post that one here. And other thing that I want to post is previous webinars. I think this is a great resource that you can find if you want to enrich your knowledge on various topics in geoenvironmental aspects. So I want to post that YouTube channel link whenever you have a chance, go to that. And there are more than 75 recorded webinars. I think it's a very rich resource if you are trying to find new research areas to explore. So because when I start sharing the presentation, I wouldn't be able to see my chat box. So I just wanted to get these out of the way, and let's get back to my presentation today. It has been very nice giving this series of presentations. Let me see. I hope these are all beneficial to you. Can somebody confirm if you can see my presentations?
Yes, sir. Yes.
Okay, excellent. So my topic today, I mentioned I work on various topics in geoenvironmental engineering. I try to showcase some of the research projects that we work on to give you an idea about the topics that we work on, and also what kind of research methodologies that we follow. So today's topic is on bioreactor landfills, design considerations, coupled dynamic processes, and modeling. So remember what I mentioned. I work on environmental remediation of soil, sediments, groundwater, and stormwater, and the waste management and landfill engineering, and sustainability and resiliency engineering, and then also geotechnical engineering. So in geoenvironmental engineering, mostly environmental remediation and waste management. So during my first day, I give you a flavor to one of the projects that we worked on related to environmental remediation. There's electrokinetic remediation. And then next day, I presented on another remediation project that we worked on. So I could talk about other remediation technologies. They're all very fascinating research projects. It's not one technology that is going to it will be a magic solution. So depending upon the site conditions, depending upon the contamination conditions, you have to choose different technologies. That's why we have to have different technologies in our toolbox so that we can apply those as needed. So you can explore other topics based on the two presentations that I gave. And then I wanted to move on that second area of geoenvironmental engineering, waste management, and landfill engineering. So yesterday I talked about biocovers for minimizing the gas emissions from dump sites or landfill sites. So today I wanted to talk about this bioreactor landfills, which has quite a bit of relevance to many places, but you have to be doing a lot of research on this topic before you apply in the field. So tomorrow I'm going to talk about tomorrow I'm going to give a presentation to something related to sustainability and resiliency. So before I get started, this bioreactor landfill work has been going on in my lab for several years. And these are the students who have worked on And I'm going to, summarize all the work that these people have done it very briefly, so that you get an idea about the types of works that we have done, and then if you are interested in exploring, you can consult the publications. So the funding from U.S. National Science Foundation, EREF, Itasca Consulting Group, CREED, Veolia Waste Services, University of Illinois, Chicago. So the funding is received from various different sources. So in my presentation today, what I'm going to do is I'm going to just give you a very brief introduction to the landfills, and then introduce you to these bioreactor landfills. It's very important to understand what these bioreactor landfills mean. Then I'm going to talk about, a previous landfill research at our university, UIC. And then I'm going to talk about evolution of new coupled thermo-hydro biomechanical model. And then, how we validated that based on the reported lab, field, and modeling studies. And then, applying that model to full-scale landfills and bioreactor landfills, and then get understanding of how the landfills will perform under regular landfill conditions and under bioreactor landfill conditions. And at the end, I'll have a closing comments. So let's have a very brief introduction to landfills and bioreactor landfills. So everyone should be aware of what a typical engineered landfill is. So this is the basic information that one has to know it. So basically, you have a ground surface. If it is possible, you can excavate down to the depth that you want. And then you basically have a bottom liner system and side liner system. You have a composite liner is a minimum. So you have a compacted soil, 2 feet thick, 10 to the power of -7 or less hydraulic conductivity. And then on the top of it is you have to have HDPE geomembrane liners. Generally, that is 60 mil HDPE. And then on the top, you have to have a leachate collection and removal system that has to be they don't prescribe what it should be, but it should be such that at no time hydraulic head, leachate head on the top of the liner would not exceed more than 1 foot. So you come up with your own design with the leachate collection and removal systems and demonstrate that your leachate head will never increase more than 1 foot. So you collect the leachate and do the treatment on site or off site. And then you place the leachate place the waste in layers. And once it fills the capacity, you need to put a final cover. And then the final cover also consists of a composite liner, compacted clay, and HDPE. And then on the top of it, sometimes you have a drainage layer, and sometimes you don't have it. But on the top, you must have a vegetative soil cover. So these are the essential components, and the design of all these things is very well established. You can look at my geoenvironmental engineering textbook. It will give you step-by-step procedure on how to select the materials, how do you decide the thicknesses, how do you do the analysis. So complete this design of landfills is kind of well established. In US, consultants can easily do this job. So these are all as per the requirements of our RCRA, Resource Conservation and Recovery Act. And same is followed by a lot of other countries. I think Central Pollution Control Board has similar regulations. So these landfills, are being designed like this, and they are constructed, they are being operational. Some landfills have been there for decades, 2-3 decades, and there is a lot of monitoring going on at these landfills. And all that monitoring data shows that the landfills as designed and constructed as per these specifications are working very well. There is no leachate migrating into the subsurface. There is no groundwater contamination, subsurface contamination problems. So, it is proven that this landfill design is the best way to contain the waste and not cause any issues with contamination of the subsurface. And leachate is not a problem, but I showed you in the last presentation with the liners, with the cover systems, even if you engineer the cover systems properly, and even if you have a gas collection system, still there is a problem of fugitive emissions. And then for that fugitive emissions, the solution is biocovers or biogeochemical cover that I talked about in the last presentation. So, okay, so this is all done. Okay, so what can we do in this one? If you are saying that, you know, these can be designed, they are performing very well, so, you know, matter is closed, right? No, then there are some issues with these engineer landfills. What are these issues? The issue, the number one issue, the main issue is the waste degrades very slow in these engineer landfills. Why? Because the main reason is we are taking out the leachate from the bottom, right? So with the leachate collection and removal system that we have at the bottom, we're taking out any leachate. We're not letting any leachate to be accumulated at the bottom. And at the top, we are putting a very watertight cover system. So there is no way infiltration of the precipitation can go enter into it. So basically, we are not allowing any water to enter into it, and any moisture that is any liquids that are, you know, in the waste, they're going to flow through the cavity to the down into the leachate collection system, and we are removing it. So the problem with that one is the waste that is in the landfill exists relatively under dry conditions. So you don't have enough moisture because all the moisture is either taken away or not allowed to enter. So, you know, for the waste to degrade, you need to have certain minimum moisture content. So the waste has all kinds of microbes. So you are going to degrade them. The organics is going to degrade by the microbes that are present in the waste. And then since you are covering it up, so you basically have anaerobic conditions. So there is no oxygen within the landfill. So you're going to have anaerobic degradation of the waste. Due to anaerobic degradation of the waste, you're going to have methane and carbon dioxide, roughly in the equal amounts, and you will have some trace H2S, trace other gases. But the waste degradation is very slow because of the moisture content. So if the waste is really slow, then, you know, it's not going to generate a lot of gas. And the settlement that is going to happen is very slow. What is this? What is the problem with this one then? So low gas generation, low settlement rates. What does that mean? So low gas generation, that means, you know, if you are trying to, you know, utilize the extracted gas for energy purposes, you need to have, you know, some confidence that you're getting certain reasonable amount of gas that is coming out consistently with time. Otherwise, you cannot operate, you know, landfill gas to energy plants. So, you know, as if you design an engineered landfill, if the waste is not degrading at a faster rate, you're not going to get good gas generation rate. Then waste to energy plants or the gas to energy plants are not going to be successful. The settlement rates, why low settlement rates is a problem? Because, you know, ultimately you're going to get this, you know, this huge amount of settlement. It could be 20 to 30% of the height of the waste due to degradation of the waste. And it, you know, if it is happening slowly, it's going to take very, very long time for the entire settlement to take place. We would like to have that entire settlement take place so fast that there won't be any settlement. So then there won't be any issues, you know, in terms of the reuse of the site. So those are the problems. So as I said, like, you know, you have a long period of time for the waste stabilization to take place. And all these landfills, until the waste is stabilized, that means you should not have any more gas generation, you should not have any more settlement. So that's what is the time that is required for that. That's called waste stabilization period. And that period is going to be very, very long because of the low moisture in the waste and low degradation. And you have to monitor the landfill as long as the waste is not stabilized. And you're going to incur a lot of costs. So if you have to monitor for a long period of time, that means I have to monitor for a long period of time, and all the costs associated with the monitoring are going to be there for a long period of time. Now, the other problem is leachate treatment and disposal. So you're going to collect the leachate from the bottom, and then you have to have a this leachate treatment plant on site at the landfill site, or you transport the leachate to a treatment facility and treat it. a lot of times the wastewater treatment facilities, municipal wastewater treatment facilities, they are not designed to treat the leachate. Leachate has all kinds of stuff. The municipal wastewater that goes from our bathrooms, that has a typical composition, but leachate, depending upon the waste that go here, that could have all kinds of metals, all kinds of organics. Now they're talking about PFAS. All these things are going to be there. And then treating that leachate on a constant basis, or disposing, that is going to incur a lot of costs for the landfill operators. And then these methane and CO2 emissions are going to be emitted into the atmosphere, and that's going to be a problem. There could be fugitive gas emissions, or depending upon how you cover the landfill, or during the filling operations, you're going to have these issues. And then it's a long-term liability, because things are going to take a long time, so you have to incur the cost for a long time, and then the site is not going to be used for a long time. So you are, as a landfill owner and operator, you're going to be responsible for all kinds of issues associated with this landfill over a long period of time. So question is, okay, it's working good, but we have all these issues. What is the potential solution? The potential solution is the bioreactor landfill. So what is it? Bioreactor landfill is exactly same as engineered landfill that I described before. Only difference is that the leachate that comes to the bottom of the landfill, instead of collecting it and treating on site, or transporting and treating off site, what we do is we collect the leachate, and then we, in a controlled fashion, we inject back into the waste. So to inject back into the waste, you could use the vertical wells, or you could have a series of horizontal wells. So basically, the whole idea is, I want to re-inject that leachate into the waste, such that the waste gets adequate moisture content, uniform and adequate moisture content, so that the degradation of the waste can accelerate, right? So what are you doing? We are taking out the leachate and then re-injecting into the waste using these leachate recirculation systems. And then one thing that we have to realize, that once you increase the moisture in the waste, right? So that's going to accelerate the degradation, and you're going to start getting the gases very quick. So you need to have an immediate gas collection system. So in a conventional landfill, you could take some time, because the waste is not going to degrade faster. You can take time to install the gas extraction wells. But if you have a bioreactor landfill operations, so you need to be ready to, you should expect the landfill gases to come out really fast. So you need to have a system to remove and use it for power generation or whatever you want to use it. So this is the bioreactor landfill. So there are here what are you doing? We are basically doing the leachate recirculation. So some people call this one leachate recirculation landfills. The bioreactor landfill is even broader than leachate recirculation landfill. In a broader landfill concept, you could actually get the liquids from offsite and inject it, not necessarily limited to leachate that is collected at the bottom. So that's kind of a broader meaning of bioreactor landfill. So the leachate recirculation is one way of operating the bioreactor landfill. But bioreactor landfill in general, it refers to adding any type of liquid. That's where the problem comes. Recirculating the leachate is not a problem. So in the US, regulating agencies will give you permission to do this one at all landfills. But if you suggest that I'm going to get some, other liquids to inject, then regulating agency is very concerned about that. What kind of liquids you are bringing? Or they are going to have, worse stuff than leachate that you're generating. So what is going on in the US now is many landfills operate this leachate recirculation. So that's also, from my point of view, that's also bioreactor landfill. But we cannot use, other liquids for recirculation unless you get a special permission to operate that way. And the regulating agency will monitor it very carefully in terms of what kind of a liquid that you're injecting it, and what is happening with this situation. So I need to make sure that you are clear with bioreactor landfill versus leachate recirculation landfill. And doing this one, you're going to get a lot of benefits. So it's going to promote rapid waste decomposition and enhances the gas generation rate, increased gas to energy conversion, high settlement rates. Remember all the things that I said, problems with the conventional landfills, they can be overcome with bioreactor landfills. And is early waste stabilization. Typical waste stabilization that could take maybe 35 years to 50 years. But if you operate a landfill as a bioreactor landfill or leachate recirculation landfill, you can be stabilizing within 10 to 15 years. So substantial, like a decrease in the stabilization period, and all the benefits of shortening that stabilization time. There are a lot of other secondary benefits. Reduced post-closure monitoring costs. So you're stabilizing early, so you don't require to monitor for a long period of time. So you're going to save a lot of money for that one. And then, when you are collecting the leachate from the bottom, that has a lot of organic strength, and it's very, difficult to treat it. So when you recirculate it, the organic strength is going to decrease, and then makes it much easier to treat it. And you don't have to send the leachate to treatment, or you don't have to do the treatment. So basically, you're collecting it and injecting it back. So that's going to save a lot of costs for the landfill operators. And then land space reclamation for fresh waste. So once you degrade the organics by these bioreactor landfills, what you have is inorganics. And then probably you can do the landfill mining, and then do the recovery of all the inerts and other things, and then you can reuse those inerts for beneficial purposes. So that's what the presentation that you heard from Supriya before I started presenting. So as I told you, the landfill leachate is the one that is commonly allowed to be re-injected. But you can use, in theory, you can use the industrial wastewater or sludge, biosolids with a high moisture content, or you can use a groundwater or stormwater, right? But as I said, the regulating agencies, authorities will have no problem using the landfill leachate that is generated at the same landfill. But if you want to use all these things, you need to get a special permit from regulating agencies. And there are very few landfills that operate in a true landfill, true bioreactor landfill sense, using these other liquids other than the leachate. So keep that one in mind. The leachate recirculation is important. So what ways that you can introduce the leachate into the landfill? So there's a drip irrigation. You put the waste, and then you have a drip irrigation system on the top. Spray head application, during the filling. Tank truck application, you can get the leachate collected and put it in the truck, and then take it to the top of the landfill. As the waste is placed, you can spread the leachate. Sometimes you can create the ponds or infiltration ponds on the top of the waste, or you can have a shallow surface trenches, and then you put in your leachate in that, or deep surface trenches. You can put those things and put it in there. So these are all like a leachate injection that is done from the surface. So they all have some advantages and disadvantages. What are the other options? Other option is the vertical wells. So you can basically dig a well into the ground, into the waste, and then you put a slotted pipe in that, and put some kind of a filter pack. It could be gravel, or it could be any kind of a permeable material around it. And then, you inject the leachate through that one. So these wells are located at different depths, and screen depth, has to be varied. So that, you place bunch of these vertical wells in the landfill waste, and then you inject it. So it's typical drilling, and then putting that the slotted pipe, and then putting the filter material, and then sealing at the top. You want to make sure that you get that sealing done. And then this also has advantages and disadvantages. So these have to be installed after you fill up the waste in the cell, in the landfill cell. The other way is horizontal trenches. These trenches have to be installed during the waste filling. So let's say you put the waste up to a certain depth, then you dig a trench, and then put a permeable material around it, and then you have a slotted pipe, and then you inject the leachate at one end, and with the pressure or with the gravity, the leachate gets distributed in the trench, and then from the trench it goes into the waste. So that's is done, and then you put the waste on the top of it, and then you have another layer of horizontal trenches like that. You can have multiple trenches, and these trenches have to be spaced horizontally, and then you have different levels of trenches as the depth increases. So these also have advantages and disadvantages. So then other one is the drainage blanket. So the drainage blanket is, okay, you put a waste up to certain height, and then you put a thin layer of permeable material, and then you have a pipe going through this material, and then you introduce the leachate from that pipe. So once the leachate comes into this layer, this is more permeable than the waste, right? So the leachate is going to flow horizontally, and then it's going to flow vertically through the waste. So basically you have spreading of the leachate over a large area and infiltrating into the waste. So this is called drainage blankets. Again, these have to be used during the filling stages. Only vertical wells are the ones that you can use after the waste is completely placed, and then you drill the wells and put it in these things. The horizontal trenches, surface methods, and the drainage blankets, they all have to be done during the waste filling. So, but the main problem with this one is you need to have this drainage material. People started using some kind of shredded tires, glass cullet, any kind of waste material, spread it, and then use that one as a drainage blanket. And that can be done, but you need to have a lot of coordination to do this one. But most commonly, what we do is use the horizontal trenches if you planned ahead from the beginning. Otherwise, you use the vertical wells. Now, when you are designing these leachate recirculation systems, you need to think about many other issues. So leachate volume to be circulated, how much moisture increase that I need to have, so that what is the initial moisture content of the waste that you have, and then how much increase of the moisture that you want to have, right? So how much is the moisture taken up by biodegradation and the source of moisture supply that you have, and the rate of leachate injection. So how much leachate that you have available, how much you have available, and then what is the capacity of pumping capacity of the leachate leachate recirculation systems, and then waste hydraulics. What is the porosity and permeability of the waste? So you cannot inject as much as you want, because the permeability of the waste is maybe low. So the permeability could decrease with the waste degradation, or the permeability of the lower layers may be lower because of the overburden waste that exists. And the type of leachate recirculation system. So what kind of system that you have? So you have a different leachate recirculation systems I showed you. And the configuration and layout of leachate recirculation system. So spacing, both in plan and depth. If you are using vertical wells or horizontal trenches or drainage blankets, you need to have an idea how many of them I need. What is the spacing, depth-wise and as well as in the plan view. And the stability of leachate recirculation system. You want to make sure that those pipes that you place to recirculate the leachate, they are stable. Okay, but if they are if you have a differential settlement and if these pipes break, then that line is not going to work. So you're not going to distribute the leachate uniformly. So leachate injection pressure. So how much should be the injection pressure, right? So think about it, especially near the edges, near the side slopes. If your leachate injection system is close to the slope and you are injecting under high pressure, you could have excess pore pressures, and then you could endanger the stability of the slopes. So you really need to make sure that you have some setback distance, and then you have a pressure within the limits so that you don't have any issues with the slope stability. And the leachate collection and removal systems. Okay, so you need to make sure that the leachate collection and removal system is properly designed, because you are circulating it, and make sure that it does not clog up. If it clogs up, the leachate collection and removal system at the bottom clogs up, then you cannot do it, because you cannot remove the leachate and then do the recirculation. The liner system has to be good, because we always have to maintain less than 1 foot of the leachate on the top of the liner, and the temperatures and chemical compatibility. So there are I will talk about that one. You're going to increase the temperatures in the landfill, and the liner should be stable under those conditions. And then leachate has a lot of chemicals, so the liner system should have a resistance to those chemicals. So all these things have to be taken into account. The slope stability is a big concern. So important thing is, when you are injecting the leachate, you're going to have excess pore water or gas pressures, and you need to evaluate the stability of the slope due to those increased pressures. And then also with the time, due to waste degradation, the waste properties are changing. The unit weight may be changing, and shear strength may be changing. So will the unit weight increase, or if the shear strength decrease, then that would endanger the slope stability. So that has to be also checked. The capping and cover systems have to be checked properly, so that we can install the gas collection systems properly. You will have the capping and cover are stable under this accelerated displacement that's happening. Gas extraction collection systems, as I said, gas is going to generate really quick. So you need to have gas extraction wells, and then you need to design it to be able to extract all the gas that is expected to generate. And then you're going to have increased gas pressures, and then the gas flow under increased moisture in the waste. So you have a moisture and the gas together. So you need to look at both options. Leachate availability is the big issue. So do you have enough leachate in the landfill? So in some landfills, you have a lot of leachate that is generated, and at some landfills, you don't have enough leachate. So you really want to put in more leachate into the waste, so that your moisture content can increase really fast. But you don't have enough, or if the leachate recirculation system is not efficient, then you will not be able to distribute it. Leachate injection operations. So how are you going to inject? Okay, you have these horizontal trenches and vertical wells. You're not going to inject leachate into all of them at the same time and continuously. So you're going to put decide mode of injection: intermittent, or continuous. Maybe basically for some period of time, you will put it along certain lines of leachate recirculation systems, and then you stop it, and then inject in other lines of leachate recirculation system, and probably repeat it several times. So that's what it's going to happen. And you have to have an operator. Operator has to kind of feel it. Where is the excess moisture going? If you put excess moisture at one location, so that's the place it's going to degrade most, and you could have excess gas pressures, but there is other places it may not be happening. So the on-site operator will play a major role in these bioreactor landfills. The materials used for construction of leachate recirculation systems, I mentioned. So you need to use the materials that have a strength. They don't, fail during operations. Chemical compatibility is an issue. And you need to have a drainage media around the pipes. What kind of drainage media you want to use it? Gravel or shredded tires or glass cullet, any waste material that is chemically compatible and permeable can be used. And leachate mounds, when you are injecting it, the waste is highly heterogeneous. So you may have pockets of waste that is low permeable. So if you're injecting the leachate, and that all that leachate might go and accumulate on the top of that low permeable waste zone. So you have a perched leachate condition. So you have to kind of look at all those aspects. Gas extraction, you need to look at accelerated gas production, and since you are putting the moisture, so the moisture could be coming along with the gases, and then of course if you saturate it, you're not going to get any gas. So you need to optimize that gas extraction. Seepage control, you're injecting the leachate, right? And then you don't have any control. It's highly heterogeneous. Generally, the lower layers will have a low permeability. You have basically stratified, waste with different hydraulic conductors. So leachate tends to move horizontally, and if it comes to the edges and then it seeps out, then you have a problem. So the leachate is not contained. The water problems, you're accelerating the degradation, and we have a lot of H2S that is generated. Then it's going to smell bad, and that could raise a concern. Differential settlements is a big concern, because if you don't distribute the leachate uniformly, or if the waste is not uniform, then you're going to have a differential settlements that's taking place. Leachate collection system has to perform really well. Inspection and recording has to be done constantly. And then one has to monitor during all these operations how much leachate is generated and what is its quality, that you have to look at it. How much you are distributing it, what are the pressures, that needs to be monitored. And the waste condition, how is the waste degrading, what stage it is, how the properties of the geotechnical properties of the waste are changing with the degradation. All these things somehow you need to monitor and take into account if there are any issues with those changes. The waste settlement, rate of settlement is going to be faster. In a way, it's good, because if you are operating these bioreactor landfill operations, and if the waste is settling and you didn't put the cap on, generally they don't put a cap on, they put a temporary intermediate cap on the top of it. So the waste is going to degrade, and then waste is going to settle. That means you can bring in more waste. So you can, after some time, you can take out the intermediate cover and then put the more waste and then put the final cover on the top of it. So landfill guys like it, because you can add on additional volume of the waste on the top of the settled waste. The gas quantity and quality needs to be monitored with the on-site probes in the gas extraction wells and around the landfill, and the temperatures have to be also monitored. And then in terms of the cost, right? So you have to think about traditional landfill. The cost of construction for a traditional landfill is going to be slightly lower than bioreactor landfill, because in the bioreactor landfill you have this additional leachate recirculation system that you have to build on. And then if you look at that, operation and maintenance is going to be small. But in case of bioreactor landfills, constantly you're pumping in that leachate recirculation, the cost is going to be high. What makes a lot of difference is the leachate treatment. In a conventional landfill, you are going to extract the leachate and then treat it. That cost is going to be really high. Whereas in bioreactor landfill situation, you're not treating the leachate at all. You're just taking it out and putting it back, that one. And then, you can see the proportion of the post-closure care is going to be, compared to this one in terms of the overall cost, it could be around 20, and this is going to be 30%. But that's going to be in a very short period of time. So I'm not comparing both of them, but within the total cost of, traditional landfill versus bioreactor landfill, or, sometimes we call sustainable landfill. So how the cost proportions change, okay? So those are the things that I mentioned in this one. And then, energy revenue. So in a conventional landfill, you're not getting these reliable amounts of gases, so you don't produce any energy. But in case of bioreactor landfills, you can, with the confidence, you can create energy. from the collected gas. So that can create some revenue and can offset the additional costs that are incurred by installing leachate recirculation systems and operating the bioreactor landfill. So you're going to have a lot of potential savings, reduce leachate treatment, landfill air space gain. Again, as I said, like if it's settling due to bioreactor landfill operations, so that all that volume, extra space that you can put the waste, and that's going to generate the savings. And landfill mining, you could do it. Material reclamation, you can do it. This is kind of a plant where they're producing the energy. And as I mentioned, once you degrade the waste, we degrade the organics, you have all the inorganics. And then, landfill mining makes sense. Your material processing, material recovery, and beneficial use of all these materials for engineering applications makes sense. So until we get rid of that organics, then you cannot really do the landfill mining. So in India, at these legacy dumps, right? So these have been there for a long time. Aerobically or anaerobically, all organic matter has been gone, degraded. So you have basically inerts and with no organics. But if you are talking about new waste that is coming to the landfill, as Supriya showed, it's about 45–50% in India. In the US, it could be about 60–65%. So you have substantial amount of organics that is there in the waste that is being disposed initially in the landfill. So that needs to be reduced. So unless that organic content is reduced, you cannot really do the landfill mining. So this is great, right? Bioreactor landfill is great, but there are a lot of issues that have to be considered carefully compared to the traditional landfills. So in terms of practical challenges, if I want to use the landfills, bioreactor landfills, there are some issues that we have to be extremely careful. The first one is optimizing the liquids injection. How can we inject so that we get uniform moisture distribution in required amounts? We don't want too much of excess moisture, and we don't want heterogeneous distribution. So some places you have moisture, some places you don't have it. So how do we achieve that one? So how do we optimize that leachate re-injection into the waste so that we can get uniform and adequate moisture distribution? And if you are very aggressive in leachate injection, or if you don't plan properly, you could be causing the slope stability failures, slope failures. That could be a huge shame as an engineer or operator. So you're trying to do this novel technology, and you didn't consider the liquid pressures and excess water, and then you cause the failure of the slopes, and that you don't want it to happen. Any slope failure will be very difficult to fix it, and delays and costs associated with that one. Now, when you are doing the bioreactor landfills, you're going to get substantial gas and substantial heat, and as a result, you have a temperature, and then substantial leachate generation. So you really need to think about, okay, I'm going to have all of these things in substantial amounts. How do I manage this? So how do you need to predict these things too, right? And then, things are going to vary spatially and temporally. With time, with space, moisture is going to change, sediment is going to change, temperature is going to change, properties of the waste are going to be changing. I really want to understand how the waste is going to degrade and consequences of all these things. You need to really need a predictive model so that we can assess all these things. There's no way that you can go to the landfill and monitor for all these things. You can monitor to some extent, but you need to have some kind of predictive model so that we can look at all these things. And moreover, you have a composite liner at the bottom. You are thinking about leachate recirculation in the waste and doing all the things in the waste, but you have a waste and liner interaction. What do you mean by liner? You have a geomembrane, right? You have a geomembrane, and then below that you have a compacted clay, and then on the top of it is you have a leachate drainage layer, leachate collection and removal system. So that liner, that you have a geomembrane and compacted clay, you should not be affected by all these bioreactor landfill operations. One of the main concerns is that temperature. because of the accelerated biodegradation, you're going to induce the high temperatures in the waste. And if you have high temperatures, what will happen to the geomembrane? Okay, and maybe geomembrane and the compacted clay interface strengths, will it decrease, right? If it decreases, then initial assumption was you had some values. Now during the operations, you have different values, and if they are going to be lower, and that's going to endanger the stability of the liners and cover system. So that's important thing to look at it. Now the question is, okay, you want to do the landfill bioreactor operations, then the question is, somebody will ask you, okay, I want to go to the bioreactor landfill operations. Okay, what would be the waste stabilization time? How much time it's going to be? How fast it's going to happen, right? So you need to be able to predict. So if the regular landfill is taking 35, 40, 50 years, okay, how much it's going to take this bioreactor landfills? Again, it depends upon your operational conditions, your leachate recirculation system, and all those things. How can we predict that one? So you need a model to predict these things. So here is the interesting aspect. Landfill operators like operating their landfills as a bioreactor landfills because they see a lot of advantages, including including saving the costs for leachate treatment, right? On the other hand, if you look at the regulating agencies, they like bioreactor landfills because if the waste degrades faster and everything gets stabilized faster, all the contamination issues, gas issues are addressed very quickly, they are relieved. We will not have any, once the waste is stabilized, we will not have any environmental issues. And a lot of people are worried about integrity of the liner systems over a long period of time. I don't know if these liners will perform as well as as built initially in a long period of time. So if the conventional landfill is going to take long period of time, during that time, will the liners work as efficiently? So if you are accelerating the degradation faster, if you're looking at a short-term period, within that short-term period, maybe the liners will be fine. Liners and cover systems will be fine. So that's kind of the issue. So the landfill owners like it, and regulators like it as bioreactor landfills. The main problem or main concern for both sides is doing these things in a proper way, not get into complicated issues like a slope failure or liner damage. So all kinds of things like this. So we want to go for bioreactor landfills, but we have to be worried about all these things. And why we have to worry about all these things, right? If you think about the waste as biodegradable solids, that's organics, and then you have inerts, right? And that's like a porous media. And within the pores, you could have a leachate. And within the pore, within the air voids, you could have air or gas. Basically, generally, we are talking about landfill gas, landfill leachate in the pores, right? So like a soil mechanics, in soil mechanics, we consider the soil is a three-phase material, right? So the solids, liquids, and the gas. So the gas and air and liquid, air and water that we consider. But instead of air, we have a gas, and instead of water, we have a leachate. But instead of just calling the solids, we have inert solids and biodegradable solids. So this makes it a little bit more complicated because we are injecting the leachate, right? So you need to look at how the leachate is going to, leachate and gas is going to flow through it, how the moisture is going to be distributed, how the liquid and gas pressures are going to be generated. So just to, we have the waste and we are injecting the leachate, and you have these hydraulic issues, right? And then as the moisture is distributed, moisture is increased, then you're going to have increased microbial activity. This comes out of biochemical processes kick in. So due to microbial activity, you're going to have solids, some organic solids are converted into gas phase, and then the gas is generated, and also that could affect the leachate characteristics in this one. So these things are happening. As the moisture is introduced, you're going to have all these biochemical processes are going to happen. due to these biochemical processes, the biochemical reactions that happen, that generate the heat. So then you're going to have a heat generation, and then heat is going to be distributed within the waste, and then you could have some heat loss. So you have these thermal processes happening due to the biochemical process. Now the solids are lost, you have a moisture, you have a heat, then that's going to affect the mechanical response, right? So the deformation, strains, stresses, constitutive behavior, strength is going to change. So the mechanical things are going to change. But this is not steady state, right? Now, as you increase the moisture, and these things are going to change. As a result, these things are going to change. These, hydraulic, biochemical, thermal, and mechanical. So these are like changing spatially and temporally. So it's you can imagine the dynamics of these much more complicated than any soil systems that we can think of, right? So these are all interrelated. So hydraulics is affecting biochemical, biochemical is affecting thermal, thermal is affecting mechanical, mechanical is affecting hydraulic. But even hydraulic is going to affect thermal, and then biochemical is going to affect mechanical. Can you see that? So how complicated these things are, right? So, but that's what is really going on in a bioreactor landfill, much more in an aggressive way than typical landfill scenario. So we have been doing research at UIC, University of Illinois at Chicago, in my lab for over 2-3 decades. Okay, so ever since I started at UIC, I've been working on this problem. We did several field investigations. We went to the landfills, we drilled the boreholes, and we collected the samples of fresh samples that are coming to the landfill, and drilled at different locations, collected the samples at different depths. We try to figure it out, what are the fractions that are available, compositional differences with depth, with time, all kinds of things we did. So we collected large size samples. We do the characterization, particle size analysis using huge sieves, big sieves, and index properties. We do that one. And then in the field, we wanted to know how the leachate is being distributed, how the waste is kind of changing. We try to investigate that one using the ERT, electrical resistivity tomography, and using the in-situ moisture conditions. And then we tried different types of geophysical methods. The idea was, hey, can we use any kind of a geophysical, non-invasive techniques to understand how the leachate is being distributed, how the waste conditions are changing, right? Because otherwise, if you have to drill the hole and collect the samples all the times, all different locations, that's really too much. Found, for example, EM. I can walk around with the EM on the landfill, and then I should be able to read shear wave test, seismic test to determine the dynamic properties of the waste and how they are changing with bioreactor landfill operations. You cannot do a lot of things in the field. So lab investigations, people question a lot about doing anything with the waste in lab setting. For example, inerts and fines that are fine. Those are like they are like soil-like materials. All the testing equipment that we have can be used for lab testing. But when you really look at the waste, the fresh waste that is going to the landfill, there's no way you can test it. Lab testing is impossible. But we have to do something. So they're not really true representative, but we shred them and then try to make our lab equipment as big as possible, or use the resources that we have, and we do the testing. And we always realize that, okay, in the field we have a different size distribution, things could be different, but these lab investigations kind of give you the feeling, not necessarily the true reality. So we created this anaerobic cells. We degrade the waste at different degrees of degradation, and we look at, hey, if the waste is degraded at different levels of degradation, how the geotechnical properties are changing, right? So we look at the leachate chemistry, and we do the sampling and testing at different DODs, degree of degradations, and we do the geotechnical testing, hydraulic properties, shear strength, compressibility. With the lab testing, you can control the the level of degradation, and then take out the sample and test it. So that way you can know how the waste is changing its properties as the waste is degrading, right? So then we did substantial amount of lab testing, and after that we embarked on numerical modeling. First thing we did is a simple settlement modeling, constitutive modeling. Then, that's okay for conventional landfills. But when you talk about bioreactor landfills, where leachate injection is happening, so how the leachate is being distributed, that's the hydraulic modeling we had to do it. And then we had to look at slope stability issues as a result of increased moisture distribution and increased pressure distributions. And then can we come up with a design guidance to look at how much should be the spacing and all those things for the leachate recirculation systems. And then can we do the hydromechanical modeling so that as the leachate is being distributed, what is the sediment that is taking place. But in reality, what we have is a thermo-hydro-biomechanical. As I showed you, the dynamic processes, we need to couple all of them to do the realistic modeling. So we have been doing all these things, and as I mentioned, I gave you the link to the publications. You can find many papers that we wrote on all different aspects of these field investigations, lab investigations, and numerical modeling. What I want to show you is development of this coupled thermo-hydro-biomechanical model. I don't want to go into a lot of details, but kind of give you overview of this model and how it could be utilized to understand the bioreactor landfills in field scale. So this is a multi-year effort. Initially we said, okay, let's look at only flow-only model. Okay, flow with a simplistic, mechanical model in there. We're not going to put it any biodegradation. We're not going to put any thermal issues. So the whole idea is, okay, let's look at the system and we are injecting it. How do we optimize the leachate recirculation system? So this is the PhD thesis of my student in 2012. The goal is to develop two-phase flow hydraulic model to predict leachate recirculation system, leachate recirculation in landfills. So what we did is a two-phase flow modeling. So you have landfill gas and leachate, right? And we have assumed the Darcy's law is applicable. We have capillary pressure, relative permeability. They are the functions of saturation, and we use the Van Goghen function. And biodegradation, we assume negligible. And then we use this permeability relationships. And then we use the Darcy's law for multi-phase flow for leachate and gas. And then we have this constitutional laws. Based on this, we can calculate the saturation and pressures of liquid and leachate and gas. Okay. In this one, we have a mechanical model. Basically, we have a Moore-Coulomb model in this one as a default. And the way that we use is this, the pressure changes will cause the change in the effective stress, and that the effective stress is taken into account in calculating the deformation. So it's a very simple way of accounting for mechanical aspects. So the Moore-Coulomb limited hydromechanical modeling was done with this approach, Moore-Coulomb failure criteria, but predominantly we're focused on hydraulics. So we did this one. Okay, then we said, always in modeling, validation is important with lab results or with field results. So for this hydraulic modeling, we looked at the literature, and we did our modeling. We did testing also, but we didn't do the large scale testing. We did the small scale testing. And in the literature, we found out that in UK, they had this big, cell, look at this cylindrical drum. They filled with the waste. You look at the size of this one. This is the person here, and this is a huge one. So they fill it with the waste, and here you can have a representative waste. And then they compressed it, okay? So this is a 2 meter in diameter, 2.5 meters in height, and they were compressing it. As they're compressing it, they noted the normal stress, and they measured how the volumetric moisture content of the waste is changing. And they were also looking at the settlement in this one. So we could model that one. All our modeling was done in FLAC, and we did this. Of course, we had to create our own subroutines in fish. We had to create a fish code for incorporating our specific features. So then we applied that one, and then see applied stress versus volumetric moisture content, and it was able to capture reasonably well. And then we looked at what other studies are there. So this Oliver and Burke, they did again very uh, interesting way, and with extensive monitoring. Again, they have this tank square cell, 1 meter by 0.98 meters, and they fill it the waste inside, and then they add moisture initially, and then they try to load it with the increasing the vertical stresses. And they were monitoring different aspects of like a stress strain and then moisture. And then we applied this model to these experimental conditions, and we were able to predict reasonably well. And then we looked at another scenario, another reported study. They had these big tanks to fill them with the waste, and they were doing the leachate injection, and they didn't apply any load on the top, but they used these neutron emitters detectors for looking at the moisture variation across the depth. So we modeled the same thing, and at different times, they measured the moisture through the entire profile of the tank, and then comparing that one with our model, pretty reasonable agreement was found. Again, we have we try to find as many cases as possible to see whether our model is reasonably good or not. Again, this is another study. Staub did it. Again, we plotted these results, the cell height and versus moisture content. What happens at different times during the different moisture conditions, induced moisture conditions in the waste. Then we looked at some modeling cases. Some people have done modeling, or also like some field scenarios. They looked at it. We wanted to look at those conditions also. So this was in the field. This Kire and Hyder, they had a drainage blanket. So they put a pipe in there, and they injected the leachate, and they tried to see how the leachate is being distributed horizontally and then into the waste. So we exactly simulated this one, what they have done in the field, and then we were able to compare how much is the distance leachate could migrate. And in the field, they found 25 meters, and our model showed 23.5 meters. So which is very close. So that's the only study that we could find in the field. And then we looked at, okay, anybody else did any hydraulic modeling? And we found some studies, they used the Sutra model, and they assumed this hypothetical scenario for hydraulic flow modeling. They used the horizontal trench. And then we did the same thing, and we were able to find the same results that they found with the Sutra modeling. And then these guys, Hyder and Kire, also did the modeling with the Hydrus 2D model. And again, our model and their model were very close. So they did it for horizontal, trench, and then they did for the vertical wells, and we were able to match exactly the same thing with our model. So the same thing with the drainage blanket. So this is the hydraulic modeling. That's like the first phase of our research. That was like a one-page thesis. Like, it's a lot of effort. Sounds simple, but it requires a lot of patience, a lot of dedication. So these papers are there. I gave you the link in the chat box. Click that one, and you can search with the keywords, and you should be able to find all these papers, the validation and other things. Now, then we said, okay, let's take a next step. So we have a hydro, little bit of mechanical, but let's make it a little more, bio is very important to consider, right? If we are looking at the time-wise, the biodegradation is important to consider. So here, what we wanted to do is incorporate bio aspects into our hydromechanical modeling. So the two-phase hydraulic flow model is kind of the same. Whatever we have done during the first phase, when we were doing the hydraulic modeling. That's the same governing equations that we have. The mechanical modeling is also same. We use the Moore-Coulomb criteria. There's not much change. Again, this was used in the first phase also. What is new was, can we combine, this is the same thing that I mentioned, how we take the pore water pressures, pore gas pressures, and calculate the effective stress and use that effective stress in our mechanical model that will induce the strains. The biodegradation is the new part. So how did we start this one? So for the biodegradation, the most common model that is used for biodegradation of the waste is the first order decay kinetics given in US EPA's LandGEM model. That's kind of a very commonly used model for gas prediction. I said that we can use that model to predict the gas generation. So we use that model. But in the model, they don't have effect of the water content. What we did is we modified that one so that we can incorporate the effect of water content on this decay constant. So decay constant is now function of the water content. That's kind of a new add-on that we did. And then once you do that one, we can predict the gas generation. And then what we did is we could calculate, what is the methane that is produced, and then we could calculate the maximum methane potential. Any waste that you have, there is a standard test called, biochemical methane potential, and you can take the waste and run the test, and then that gives you the maximum methane that is possible if you have idealized conditions. So based on calculated methane, and then what is the maximum methane that has a potential, that will give you a degree of degradation in terms of this definition. So you have generated on DOD is 50%, means only 50% of the total methane that could be produced has been generated like that. So then DOD can be used. And then once we have a DOD, what we did is, remember we did all lab experiments on waste that is degraded at different levels of degradation. We used all those lab test results to create this relationship. How the unit weight is going to change with the degree of degradation, how the permeability is going to change, how the shear strength parameters are going to change, how the stiffness and all this or shear modulus moduli are going to change with the degree of degradation. So we have these relationships. What we did is once we took the DOD and we put the DOD into these relationships, and we get these different properties. So when we were, doing this modeling, we will run for a certain period of time and calculate the DOD, and then from the DOD we change the properties of the waste based on these relationships and continue the modeling process. We are considering that way. So this is kind of the sequence. We do inject the leachate, we do the hydraulic modeling, and then we do the biodegradation modeling and combine with the mechanical modeling and increase the time period, and then we repeat this whole thing. So this is kind of a hydro-biomechanical framework that we generated. Now, again, once we did this one, okay, how do we validate if this is a good model or not? Then we looked at the literature. This Stab in France, they did this large-scale experiments with extensive modeling of the leachate distribution and settlement and the degradation aspects. So we were able to model with the time how the moisture content is changing, with the time, with the overburden stress, how the vertical strains are increasing in terms of the initial strains versus with time, how the creep and biodegradation are affecting the settlements. And you can see the model results are pretty good. Then we looked at other study that was done in the field. These guys went into the field, and they dug this created these big lysimeters with the waste, and they characterized all the waste, and then they started leachate injection into this waste, and they were able to monitor different aspects. So we looked at the same things with our model versus the field monitored results in this lysimeter. You can see this. This is the peak outflow of flux per area versus what they measured. So we are underestimating so with any given elapsed time, the model was giving the less outflow compared to the measured values there. But if you look at the time-dependent compression, that's pretty reasonable agreement in this one. Okay, so we got the confidence that we validated with the controlled lab experiment and controlled field experiments. Okay, whatever predictions that we are getting, they are pretty reasonable. Why don't we apply it to a large-scale model? So we're basically taking the 2D cross-section of a real landfill. This is the landfill that exists close to a Chicago area, and this is where we did all the field investigations, and we got the samples from this landfill to do our lab investigations. So this is the subtitle D, engineered landfill. You have a liner system at the bottom that is properly designed. You have a cover system is designed properly, and during the placement, they put these horizontal trenches. These are the horizontal trenches that for leachate recirculation. So we basically did a parametric study on system variables. We listed very different things and see what response we get. So the modeling framework is given, and the modeling model validation are given in some other papers. So you can see all these papers. We did also heterogeneity assessment based on the probabilistic analysis. So you can find all these papers in that link that I mentioned. So that was done, but we are not happy. Why we were not happy? We didn't really truly couple, hydro, biomechanical, and we needed to, combine the thermal aspects. So we totally ignored the thermal aspects. So here we wanted to, add the thermal and create a model. So what we did is in this, we worked with Cal Poly researchers who worked extensively on modeling thermal aspects of the landfills, and then we took their formulation in terms of heat transfer, volumetric heat generation, that empirical equation that they gave, and then the surface ground temperature, how they assumed, and then gas production rate based on, again, US EPA land gem model. And then in this one, the decomposition, rate of decomposition K, what we did is we made that one as a function of saturation and the temperature. So FW is represent the water fraction, and then T is the temperature. So this is our contribution. So we incorporated this into this so that wherever the moisture is different, there's degradation rate is different, and the temperature is different, and then this degradation rate is going to be different. So the degradation of the waste is function of moisture and the temperature. So the temperature is predicted from these three equations, right? And we put that one in there in our model, add on those temperature module. And then you can see, the model temperature at different depths in the landfill: 1 meter depth, 7 meter depth, 10 meter depth, 13 meter depth at a landfill where they actually measure the data. This is the field measured data. They put a thermal sensors and they measure the data, and then we model the same thing and then see the predicted responses, predicted temperatures versus the field measured temperatures. Excellent performance, right? Excellent matching. And then, okay, once we have that one, with our model, we can look at what is the effect of the temperature. So we are modeling the landfill. Okay, if you know temperature effect, with temperature effect, and conventional landfill. So the last one is the conventional landfill. So, and then with the bioreactor landfill with the temperature and not considering the temperature, how these things are changing the methane gas generation, how they're changing the surface settlement, right? This is the conventional where you don't inject the leachate, nothing. If I bioreactor landfill, but with the temperature, accounting the temperature versus not accounting the temperature. So those are the things are considered here. So this is the paper that looks at this one. Now, if you look at this, all this work was done. We were happy, but not very happy. Why we are not very happy is, temperature is taken in terms of empirical way. And then biodegradation is based on the USCPA land gem model. That's the empirical way. So, we have a thermal process, biological process, and then mechanical process is basically more Coulomb. That's a simplistic constitutive model, and that may not be valid for material like waste. So we thought, there should be a way to pursue this modeling through a fundamental approach. Okay, how can we not use these empirical approaches, but let's look at the fundamental basis and incorporate thermal, hydro, biomechanical model. So for this one, what we did is we developed a fundamental biochemical model. So instead of land gem model as a simplistic empirical model, we developed the fundamental biochemical model. And then we, instead of using that empirical thermal model, we developed a fundamental thermal model. And then we developed a constitutive model. Instead of a more Coulomb model, we wanted to use something that better represents the waste sustained behavior. And then, of course, all those things are integrated with the two-phase flow model. And two-phase flow model, we didn't change anything because it's fundamentally, formulated right in the beginning anyway. So based on all these things, we got this C stands for coupled thermo hydro biomechanical, CTHBM, coupled thermo hydro biomechanical model that we got. Now, again, anytime you have a model, first thing you have to do is validate it if based on whatever the lab test data or field data that you have. So we basically, once we validate it with whatever information that we have, that can be used to predict the performance of the landfill, bioreactor landfill, you can assess the liner and cover system. So everything can be looked in holistically, right? That makes really good sense. That's close to the reality than all the assumptions that we made before. So let me go a little bit faster. So the two-phase modeling is exactly the same as what I talked about in our hydraulic model. The biodegradation model, what we did is we used a two-stage anaerobic digestion model proposed by McDougall, and advection, diffusion are considered insignificant. And then, in the waste, you have a degradable solids that could be cellulose, hemicellulose, and lignin and protein. But in our model, what we used is, okay, cellulose is going to contribute to more, is the dominant degradable fraction. And then this two-stage anaerobic digestion involves these two processes: hydrolysis plus acidogenesis, and then methanogenesis. So we looked at those two. That's the two-stage anaerobic digestion process that developed by McDougall. So we worked with McDougall on this aspect so that we are not misinterpreting his data or his model. So it was very nice to work with him on incorporating his model into our model. So this is the fundamental reaction that happens during the degradation process. And you can see how the C is volatile fatty acids, how they change with time. This M is methanogenic biomass, how it is changing with the time. And then S is the solid degradation fraction, how it is changing with the time. And the d theta is the volumetric water content, how it is changing as a result of change in the solid degradable fraction. So each of those, in these terms, you can see Rg, Rh, Rj, Rk are the rate constants. They can be calculated based on these equations. And the gas generation rate can be calculated using this equation. So we are not using that land gem empirical model, but we are using these fundamental biodegradation processes and then calculating the gas generation rate. Once we get the gas generation rate, the generation rate of methane is, applying the enthalpy, we are able to calculate this heat generation. Again, this is, more like a fundamental. We're not using any empirical equation for the heat generation. So it's coming from the biodegradation and how much is the heat generated by biodegradation. We're getting that one. So now, the thermal model that we have is based on, we can generate the heat from here, right? We have the heat generation from here, and that can be used now, apply the balance of energy, specific heat capacity, heat conduction equation. So the anaerobic digestion is the one that is generating the heat, and that heat is going to be distributed through conduction and convection. Only conductive heat transport is considered. We didn't consider convection. The effect of that could be seen in the future, but the important information here is that the microbial growth rate here is a function of FT. FT is the function of the temperature, and these equations are given by some other researchers with extensive lab research. If you have a temperature between 0 to 37, you have a different equation. 37 to 47.5 is different, and greater than 47 is different. So this is a temperature feedback. So if the temperature is more, and then this microbial growth is going to be different, and it's interlinked to that temperature generation in the waste. And this is our equation, and then we try to model with the different data points that were generated through experiments. So you can see our model, these equations can best fit the observed experimental results, which is good. So this, biochemical and thermal, they are interrelated. Biodegradation causes thermal, and thermal is going to affect the biochemical. So this is a looping, interdependency is there. So that we could be able to model fundamentally and then be able to incorporate in the numerical model. Now mechanical model. So remember previously we used the Moore Coulomb model, but we wanted to use better than that because we know that that is not really true. So total strain is given by this equation. So you have an elastic strain, there's a plastic strain, and then this is the strain with rate dependent, and this is the biodegradation induced strain. So what we did is, we looked at the literature, which models can really do this. And the closest that we could come was, in my PhD research, I did the constitutive modeling. I did, lattice, elastoplastic modeling, and I did, endochronic model or thermodynamic model. I evaluated 2 of those models for cemented sands. But there you don't have a viscous effects, you don't have a biodegradation effects. So the closest that we found is the soft soil creep constitutive model that can really model the elasto-viscoplastic strains. So we use that one. So we can get the elastic strains, we can get volumetric creep strains, and then apply that one. Basically, it's creep-induced hardening, general creep hardening. Basically, in this model, we use the cap type yield stress, and then yield criteria is given by this. So incorporating all these things, the other thing that goes into this modeling, which is unique to the waste, not to the soils, is biodegradation induced strain. The biodegradation causes the change in the volume of the voids, and more importantly, and additionally, it changes the volume of the solids, which does not happen for the soils. You have reduction in the volume of the solids because some solids are converting into the gas phase, organics are converting into gas phase, and then there's a reduction in the volume of void. So using this, considering all these things, you get a governing equation is given by this equation. And then we have a detailed methodology of how we did our calculations in the paper that you can see here. Elasto-visco bioplastic modeling constitutive model, right? So now we have all these components. We have a 2-phase flow hydraulic model. We have a 2-stage anaerobic biodegradation model. We have elasto-viscoplastic mechanical model. We have a heat conduction model. How it will take some time to understand what's going on in between these things, but they are all affecting each other. So they are all coupled. 2-phase flow is going to affect this one. This is going to affect the heat. It's going to affect this, and these are all coming back and forth. All these things are going to be affected by. So at any time, these will all play a role, and then you will know how much is the reduction in the volume of voids, reduction in the volume of solids. You can predict all the gases and all kinds of information about the waste can be understood. So coupling all of them, we got a very comprehensive model that can realistically inform us on how the landfills will perform under different conditions. So this is a kind of a new model. We want to see if it works. Again, we had looked at any lab tests that we could use. Truly, you don't have any lab testing that monitors all the things that we need, right? Temperature, biochemical processes, mechanical processes, all these things. We didn't find anything, but we found some lab simulation testing that considered the biodegradation parts. Okay, so here is one landfill, this one study that looked at these lab scale experiments, and here there is no fresh stress applied, but just they circulate the leachate and look at what is going on, in the waste in terms of the biological terms. And then there is another study that this study was done in US, this study was done in UK, and here they, were able to apply the load and then circulate the leachate and be able to look at all the things that are going on. So we try to model these things using our model. So actually, they have the data points that I show here in the second graph on the right. The data points, that is the data that we have, against the validation. So we were able to get, as close to those numbers as possible. But the advantage of the model is it can give you solid degradable fraction, methanogenic biomass, and then cumulative methane, this ratio, which were not monitored, but with the model we can predict it, right? So we can get a good understanding of how this evolution is taking place with time. And then, other model, UK experiments, we were able to match the results pretty closely. So, and then we got a little, confidence in that, that model is fine. Now we wanted to see how it can be applied to the whole landfill scenario. So again, we looked at the same landfill that we looked at before. It's a realistic landfill that exists. And then we looked at, okay, conventional landfill versus bioreactor landfill. Let's say, assume the leachate is injected into these horizontal trenches, assumed layout continuously, and injection pressure is 50 kPa. We have these 4 horizontal trenches within this configured area. And then let's say horizontal spacing between the trenches is 30 meters. So then we were able to model this. So we put all that cross section, leachate injection, everything, and we simulated the placement of the waste in layers. And then, once we put the cap on the top and then let the time pass on, and you can see how different things are, evolving. So the degree of saturation, how it is changing in a conventional landfill scenario versus bioreactor landfill. So conventional landfill, you don't see much change. Whereas in case of bioreactor landfill, saturation in some places is close to 100%. So that's the important thing to look at it. And the pore pressures in the conventional landfill, you don't see much pore pressure change, but in bioreactor landfill, you're injecting the leachate, right? So that's going to introduce the pore pressures. So that's you can see the evolution of pore pressures and spatial and temporal variation of those things. You can find these things. And then if you see the pore pressures here, the pore pressures are not high close to the slope, which is good because you will not have any slope stability problem. So this is the slope edge, and then the pressures are not high as compared to other locations. And then you can look at the solids degradable fraction. You can understand how the biodegradation is happening in conventional landfill versus bioreactor landfill, and what are the volatile fatty acids, and how the methanogenic biomass concentrations are changing in this landfill. So if you have a conventional landfills, not much is going on, you don't see much change. But in case of bioreactor landfills, you can see much change after, within a short period of time. The conventional landfill will take long time, keeps on happening. So that things will take time. So degree of degradation, how the waste is degrading, right? The conventional landfill simulation, you can see it slowly happens, more in the middle, and then it spreads on the top and bottom. So, the waste at the middle, because of the high temperature there, it's going to degrade faster. In the bioreactor landfills, again, you can see how the degradation happens fast. Now, if you look at overall, the gas production, so this is a bioreactor landfill versus conventional landfill. So the conventional landfill, you see that it's going to take long time, and that's the maximum amount you get it. And in case of bioreactor landfill, you see most of the biogas, most of the gas happens really quick, within 10-15 years, as compared to this one 30 years. And that's those things you can predict. You can look at the stabilization time. If I say stabilization time, with this modeling, I can say if you operate this thing, all the modeling conditions are correct, in 12 years, you're going to stabilize it. In conventional landfill, you have a 33 years. With the realistic modeling, I can trust that these numbers are kind of close to, reality. I mean, if my all modeling assumptions are correct. So at least, we did our best to estimate this. And then you can look at the heat generation, temperature distribution. You can look at it with depth, how temperature is changing with time. You can look at the profile. This is the landfill depth. So how the temperature is evolving, 1 year, 5 years to 40 years. So the dynamic changes from the top to bottom, they change and they swing. The temperatures swing a lot. So because of the degradation. So you can see the bell shape, belly shape distribution. That is well known. The good aspect of this temperature increase in the landfills is that high temperature happens somewhere in the middle. And when it comes to the bottom of the landfill, where you have a liner system, the temperature increase is not that significant. So the temperature effect on the liners will not be as severe because of the not high temperatures there. So we can look at all kinds of things. You can understand what is going on in the landfill, how the settlement is happening. You can kind of visualize everything that's going on, which otherwise would not be possible with the field monitoring or lab monitoring. So modeling is the only way by which you can understand the dynamics of the system. So interface yield response, right? We looked at the bottom, you have a temperature changes, moisture changes, and the waste condition changes. We looked at, along the interface, how the temperature changes. As a consequence of that, how the shear happens, the shear displacements happen. And, it shows that there's not much problem. Now, we also looked at, we considered one set of parameters, right? And then parameters could be different. We assume 25 kPa injection pressure, injection spacing is 30 meters and assumed continuous. These are not like a standard, these things could change. So, based on, the potential variability of these operation parameters, we looked at different parametric analysis. We changed the injection pressure for different conditions. We changed the mode of injection. All these things we varied. We wanted to look at if conditions are different, how will it change? So all these things are summarized in one of the papers. Now, biggest problem doing the modeling in waste or landfills, people say, okay, waste is highly heterogeneous. How can you model, right? So that's the biggest concern. You cannot have deterministic modeling because the things change. So in order to assess the variability of the properties of the waste, we did the Monte Carlo simulation. We know how the range or coefficient of variation for these different properties, right? So we looked at how they vary. What is the mean? What is the coefficient of variation? We looked at all these things, and then we ran these simulations, okay? Considering the different inputs that we looked at it, not as a fixed deterministic values, but we looked at it as the probabilistic values. So basically what we found is a deterministic analysis kind of slightly over predicts the results. That's the conclusion that we found. So that's a lot of stuff to digest. I had to rush it a little bit, but as I said, if you are interested, look into the papers with a lot of details, and I will be happy to answer any questions you have, anytime in the future after you get a chance to read those things. So in the closing comments, we have this new coupled thermo-hydro biomechanical model that will addresses all the key limitations of the previous models. And this was not an easy effort. It took us over 2 decades of our intense research effort to reach this state. And the model is validated with reported lab data, field data, and previous modeling data. And more data would be used, but more validation will be better. So anytime you have a model, more validation is always better. So we could understand the evolution of the waste characteristics. We could understand the gas generation. We could understand the temperatures, settlements, and liner response with this model. And the model was applied to realistic full-scale model, and this model can be used to allow optimization of the system variables, leachate injection well spacing, injection quantities, pressures, and more, so that the bioreactor landfill will be operated effectively and safely, right? That can be achieved by this one. Ensures the landfill bioreactor safety, allows the prediction of the stabilization time. So just the last slide is, bioreactor landfill is the way if you want to really address the sustainability in landfill engineering. So if you have a landfill and you put the waste and then covering up, walking away, people might think that, okay, you're just dumping and walking away. But in a bioreactor landfill, you're containing the waste, but also you are doing the treatment. It's like a biotreatment, in situ biotreatment, in situ anaerobic, bioreactor, a huge in situ, in-ground, anaerobic bioreactor. You are treating it actively, right? And then once the biodegradation happens, you can, you have inerts, and then you can do the mining and recycle all the materials. You have a short-term and long-term environmental protection. Energy recovery is possible because you are accelerating the gas production, faster stabilization, economic benefits. You don't have to treat the leachate, you're reducing the post-closure cost, and the land reuse. This is the only way you can, convert the waste, stabilized and mining, and then reuse the site. The community engagement and environmental justice. So you don't want to dump it and have all the environmental problems associated with that one affecting the communities around that landfill site. Even dump sites, of course, you have a lot of problems, but even engineered landfills, you don't want to have any issues. So bioreactor landfill is the way that we can engage the community, and you can explain them what you're doing, and overall you can protect the environment and also achieve the environmental justice. So the whole idea is kind of hey, instead of having a landfill and walking away, can we have a landfill cell, and then you put the waste and close it and operate as a bioreactor landfill, and let it degrade until the stabilization time is reached, and then you excavate it out, and then you mine it. And once you mine it, you created again a new cell, right? And then can we kind of accommodate more waste in there, and then keep it going like this, so you don't have accumulation of the waste, and then and then land is not being used. But if you are creating more waste, this is the way that you can have a kind of a sustainable way to manage and reuse all the waste. So that's the whole story about one of our ongoing projects. Hopefully that gave you some ideas on how these kind of research issues can be tackled. And before I end, I want to mention about today is Thursday, 7:30 is my other webinar starting. I highly recommend you to attend that webinar. So these webinars are recorded. Today's webinar is going to be on climate resilient infrastructure in water sector. It's going to be given by Professor Katerina Donoveska from North Macedonia. So if you are interested, I put the registration link there. So you have to register before it starts at 7:30. So right after this webinar, if you're not doing anything, or if you are not tired of listening to me, so join that webinar and see what she says about climate resilient infrastructure in water sector. So with that one, Nilima, I'm done for this presentation.
Thank you so much, sir. Thank you. I think ma'am lost her connection actually due to her internet issues. And I request participants to put their queries in chat box, or either they can ask.
Thank you very much, Prof, for an excellent and great presentation. My name is Thomas Jimdia, and sincerely, I enjoyed every bit of the presentation. Now, I have a little question to ask. And since you said that looking at the heterogeneity of waste and the overestimation of the model properties, isn't it possible for us to associate some properties of the waste, for example, the sizes of the waste particles, then those that are cellular and those that are biodegradable, etc., and then come up with a model that will better predict the gas production, the biodegradability, etc., just like we have the Van model, the Bruscore model, etc. Isn't it possible for us to do that, and possibly to have a software for, I'm just thinking aloud, so that when we put in those properties, we can have, to a reasonable extent, at any time and at any moisture content of the leachate, be able to predict its properties? Isn't it possible, sir? Thank you very much, Prof.
Oh, thank you, Thomas. I think it could be possible, but if you have given the set of properties and you could be able to predict. But the biggest problem is that the properties themselves are changing, right? You don't have those properties being stationary or fixed. So you need to have a model that first of all, you need to be able to predict those properties that you're saying, how they are changing with time. And then, once you have a set of properties and using in your model to predict what you want to do it. So if you have a model based on some properties, that's the thing, the evolution of the properties. And then once you know those properties, if you have a model to predict what you want to predict, that's fine. So the input parameters for the model are changing. So you can, look at my papers and feel free to email me, and we can follow up with additional questions.
Thank you, Prof. Thank you, sir.
Thank you. Anyone else?
Sir, okay. No questions. Like, it was like an enormous field lab and modeling work. Great lecture.
Is Jagdish there?
Yes, Professor.
Where are you? I don't see your name. You
No,
have
I
any
am
questions?
here.
Any questions?
No, Professor. More like ideas.
Good, good.
Should I start it? The other webinar?
I will start. Just wait for a few more minutes.
Okay.
Okay, sounds good, Meghna. So people can ask me questions or
Yes, sir.
comments. You can put some comments. I think Gangadhar has put a comment. Enormous field lab and modeling work. Great lecture.
Yes,
So,
sir.
yeah, thank you, Gangadhar.
Yes, sir.
So anybody has any other comments or questions? So just put it in the chat box so that I can look at it. Even if I don't have time to answer today, I can answer it later. If I know, I can save the chat box and get back.
Sir, existing dump site conversion into the bioreactor landfill, possibility and changes.
No.
Challenges.
The prerequisite for operating as a bioreactor landfill is you must have a proper engineered landfill. You need to, because if you put a, if you have a dump site that does not have any liner system, if you are trying to inject leachate or any other fluids into the waste, you are going to create a mess, subsurface mess. You're going to introduce all the liquids, they will go into the subsurface. How do you going to collect it? So you need to have a liner system and leachate collection system at the bottom. So the idea of a bioreactor landfills is only for engineered landfills. You need to have a bottom liner, you need to have a leachate collection system, and so you must have engineered landfill to do the bioreactor landfill operations. I know some people like start talking about bioreactor landfills at dump sites. That absolutely does not make any sense to me.
Okay, so participants can put their questions in the query form also, and you have the next webinar in 10 minutes. So will it be fine to over the session? Because you have the connecting.
Anybody has any last minute questions? So just see. I want to just give one more minute to see if people can type anything.
Sure, sir.
Okay, last chance for you to type your comment or any question.
And please feel free to put your questions in the query form also. You can put over there also for any session. Like if you have gone through later on also, so you can put there. It's fine, sir.
Okay, so that sounds good. So it looks like I did a great job. That people have any question, or
Yes, sir, you always
maybe the other way around, or maybe I did so terrible job that people don't care about asking questions.
No, Prof. No, Prof. It was quite great. It was quite great, sir. Thank you so much. It couldn't have been better.
Yeah, but now all the other people are quiet, so I'm worried about that.
Oh, thank you. It was quite explanatory. No questions.
Okay, thank you so much, Thomas. Yeah, thank you.
Thank you, sir. So shall we end the meeting, sir?
Yeah.
Like from the host end.
I want to post again that link to join the next meeting if anybody is interested.
Yes, sir.
Let me just put that one in the chat box again. If you are interested in joining that other webinar, please use this link, and then you will get the joining link. And then, as I mentioned, all the publications are available on my website. Again, if you joined later, you may not have seen my link, so I'm putting the link at the bottom for the publications. So just click that link, and then you can search bioreactor landfill, and you will find all the papers related to that. Okay?
Yes, sir.
Thanks, everyone. I'm going to see you tomorrow. Okay?
Yes, sir. We have the last day tomorrow, and Professor Ankit Garg will be the first speaker of the session, and then we'll have sir finally. Okay, sir. Bye. Bye, everyone. Good night.
Bye. Thank you, sir. Thank you very much.
Yeah.
Thank you. Hello, sir.